What happens when you try to picture the distance to the nearest star? Your mind probably conjures an image of a point of light impossibly far away, maybe even beyond the moon or past the outer planets. But that mental picture, however vast it seems, falls short by a factor so large it becomes almost meaningless to state. Proxima Centauri, our closest stellar neighbour after the Sun, sits roughly 40 trillion kilometres away. If you could somehow travel at the speed of a commercial jetliner, the journey would take more than 5 million years. The fastest spacecraft humanity has ever built, Voyager 1, would require over 70,000 years to reach it, and that probe is already moving at 17 kilometers per second relative to the Sun. These numbers communicate scale in technical terms, but they fail to convey the true nature of cosmic distance because human experience provides no reference point for such spans. We evolved to navigate forests and plains, to judge the distance to prey or predator within a few hundred meters. Our brains developed shortcuts for estimating size and separation within that narrow range. Beyond it, our intuition collapses. When astronomers discuss the universe's scale, they are not simply talking about large numbers. They are describing a hierarchy of distances so extreme that each level makes the previous one seem almost negligible. The gap between Earth and Moon is vast by human standards. The distance from Earth to the Sun is more than 300 times larger. The span from the Sun to Neptune exceeds that by another factor of 30. Yet all of these distances, added together, represent less than 1/10,000th of the space between our Sun and the next star, and that interstellar gulf is merely the first step in understanding cosmic scale. The true dimensions of the universe extend far beyond what most people imagine when they look up at the night sky. The problem begins with light itself. We tend to think of light as instantaneous, something that simply appears the moment we flip a switch or open our eyes. In everyday experience, this assumption holds true. Light travels so rapidly across the distances we encounter in daily life that any delay remains imperceptible. A beam crossing a room takes about 3/billionths of a second. Even at the scale of Earth, light circles the equator more than 7 times in a single second. But this speed, roughly 300,000 kilometers per second, is not infinite. It represents a hard limit built into the structure of space-time itself. Nothing with mass can reach this velocity, and nothing, mass or otherwise, can exceed it. This constraint transforms light speed from a mere measurement into a cosmic yardstick, the primary tool astronomers use to describe distances beyond our solar system. When we say Proxima Centauri lies 4.2 light-years away, we are stating that light, travelling without interruption through the vacuum of space, requires 4.2 years to traverse the gap between that star and our Sun. This convention provides more than convenient shorthand. It reveals something fundamental about cosmic observation. We never see the universe as it exists now. Every photon reaching our eyes or telescopes has been travelling for some duration, however brief. The Sun appears as it was 8 minutes ago. Jupiter shows us its position from between 30 and 50 minutes in the past, depending on where Earth and Jupiter sit in their respective orbits. The stars visible to the naked eye are typically dozens to hundreds of light-years distant, meaning we observe them as they existed during human history's span, from ancient Rome to the medieval period to the industrial age. Some may have already exhausted their fuel and collapsed, their light still en route to Earth, the news of their demise not yet delivered. This temporal dimension to distance fundamentally alters how we must think about cosmic scale. The universe does not present itself to us as a single snapshot frozen in time. Instead, we observe a nested series of progressively older views, each shell of distance corresponding to an earlier epoch. The nearest stars show us the recent past. Galaxies millions of light-years away display conditions from when early humans were just beginning to walk upright on African plains. The most distant objects visible to our best telescopes appear as they were more than 13 billion years ago, less than 1 billion years after the universe itself began. Distance and time become inextricably linked, two aspects of the same cosmic geometry. To grasp what 4.2 light-years actually means in physical terms, consider this comparison. The distance from Earth to the Sun, called an astronomical unit, equals roughly 150 million kilometers. This span already exceeds human comprehension in practical terms. Light covers it in 8 minutes and 20 seconds. Proxima Centauri sits approximately 270,000 astronomical units away. If we could shrink the Sun to the size of a basketball, Earth would be a small bead about 26 meters distant. On this scale, Proxima Centauri would be another basketball roughly 6,000 kilometers away, the distance from New York to Paris and back again, the solar system's outer boundary, where the sun's influence fades into interstellar space, might extend a few hundred meters in this model. Yet the next star remains on another continent entirely. This gulf exists not because stars repel one another, but because of the fundamental sparseness of matter in the universe. Stars form from collapsing clouds of gas and dust, regions where material happens to accumulate densely enough for gravity to overcome internal pressure. These stellar nurseries are themselves separated by vast reaches of near emptiness. Once formed, stars disperse from their birth clusters, spreading through the galaxy over millions of years. Gravity keeps them loosely bound to the galactic center, but their individual motions carry them along independent paths. The result is a distribution where stellar density drops to roughly 1 star per cubic parsec near the Sun's location. A parsec equals 3.26 light-years, so this density means that within a sphere containing 1 star, roughly 35 cubic light-years of space sits empty, except for scattered atoms of hydrogen and helium, trace amounts of dust, and the occasional burst of cosmic rays. The nearest stars to our Sun form a revealing sample of this distribution. After Proxima Centauri come the binary pair Alpha Centauri A and B, part of the same triple star system, at 4.37 light-years. Barnard's star follows at 6 light-years. Wolf 359 at 7.9. Leyland 21185 at 8.3. Sirius, the brightest star in our night sky, appears brilliant not because of exceptional proximity, but because of its intrinsic luminosity. It sits 8.6 light-years away, twice as far as Proxima Centauri, yet outshines it by thousands of times due to its larger mass and higher surface temperature. Within a sphere roughly 16 light-years in radius centered on the Sun, astronomers have catalogued fewer than 60 star systems. Some are single stars like our Sun, others are binaries or even triple systems, where multiple stars orbit a common center of gravity. A handful are white dwarfs, the cooling remnants of stars that exhausted their fuel millions of years ago. But the overwhelming majority of this sphere consists of vacuum, empty space containing nothing but the faint whisper of interstellar gas. This emptiness carries implications for any speculation about interstellar travel or communication. The energy required to accelerate even a small probe to a significant fraction of light speed exceeds current technological capacity by orders of magnitude. Chemical rockets, which work by expelling mass at high velocity, cannot approach the necessary speeds. Nuclear propulsion systems, whether fission or fusion-based, face fundamental limits imposed by the energy density of atomic reactions. More exotic concepts like antimatter drives or laser-pushed light sails remain purely theoretical, their engineering challenges unsolved. Even if such technologies became viable, the journey times would span multiple human generations for all but the very nearest stars. A craft travelling at 10% of light speed, an achievement far beyond present capability, would require 42 years to reach Proxima Centauri. The astronauts who departed would not live to see arrival. Their grandchildren might. Communication faces different but equally severe constraints. Radio signals travel at light speed, meaning a message sent to Proxima Centauri requires 4.2 years to arrive. The response, if any intelligent beings exist there to send one, takes another 4.2 years to return. A simple exchange of greetings would span nearly a decade. More complex dialogue, the kind needed to establish meaningful contact or exchange detailed information, would stretch across decades or centuries depending on the target's distance. This time, lag does not simply make conversation inconvenient. It fundamentally changes the nature of any potential communication, transforming it from dialogue into a slow exchange of monologues, each side broadcasting into the void and hoping for eventual response. Yet even these vast interstellar distances represent merely the local neighbourhood, the immediate vicinity of our Sun within the larger structure of the Milky Way galaxy. The stars we see with the naked eye, the several thousand points of light visible from any dark sky location on Earth, occupy a tiny fraction of our galaxy's volume. Most lie within a few hundred light-years, close enough that their light reaches us from an era when written human history already existed. The furthest individual stars visible without optical aid, rare supergiants like Deneb in the constellation Cygnus, may lie as far as 2,000 light-years away. But the Milky Way extends for roughly 100,000 light-years from edge to edge. Our Sun sits about 26,000 light-years from the galactic centre, embedded in one of the spiral arms that wind outward from the core. The stars we can see without telescopes inhabit a sphere less than 5% of the distance across that galactic disk. We observe our cosmic neighbourhood through a keyhole, glimpsing only the nearest fraction of a structure containing several 100 billion stars. The Milky Way's architecture reveals itself most clearly when we map the positions and motions of stars in 3 dimensions. From Earth, the galaxy appears as a luminous band stretching across the night sky, brightest toward the constellation Sagittarius, where the galactic centre lies hidden behind layers of dust and gas. This appearance misled astronomers for centuries. Early observers assumed we occupied a position near the centre of the stellar system, with stars distributed roughly uniformly around us. Only in the 1920s did measurements of globular clusters, dense spherical collections of ancient stars orbiting the galactic core, reveal our true location far out in the disk. The Sun circles the galaxy at roughly 220 kilometers per second, completing one orbit every 225 million years. Since Earth formed 4.6 billion years ago, our solar system has completed roughly 20 circuits around the galactic centre, passing through different stellar neighbourhoods, different spiral arm segments, different densities of interstellar matter. The galaxy's disk measures roughly 100,000 light-years in diameter, but only about 1,000 light-years thick near the Sun's position, creating a flattened structure resembling 2 fried eggs placed back to back. This geometry arose from the galaxy's formation process. When the Milky Way coalesced from primordial gas clouds more than 13 billion years ago, the material possessed some net rotation. As gravity pulled matter inward, conservation of angular momentum caused the system to flatten, just as a spinning ball of pizza dough spreads into a disk when tossed. Stars in the disk orbit in roughly the same plane, their paths aligned by this ancient rotational momentum. Above and below the disk lies the halo, a roughly spherical region containing older stars and the globular clusters that first revealed our true galactic position. These objects follow elliptical orbits that carry them far from the disk, some swinging out more than 100,000 light-years before falling back toward the galactic centre. Within the disk, matter concentrates into spiral arms, regions of higher stellar density that wind outward from the core. These structures are not fixed formations like the arms of a pinwheel. Instead, they represent density waves, regions where stars and gas clouds bunch together temporarily as they orbit. Think of traffic on a circular highway where a slower section causes cars to accumulate. The cars pass through the jam and emerge on the other side, but the jam itself persists, fed by new vehicles entering from behind. Spiral arms work similarly. Stars enter a density wave, slow slightly due to gravitational interactions, then exit on the far side while new stars enter from behind. The wave pattern rotates at a different speed than the stars themselves, creating a persistent structure, even though individual stars spend only a small fraction of their orbital period within any given arm. The galactic centre presents an environment radically different from the Sun's neighbourhood. Stellar density increases by factors of millions as you approach the core. Stars crowd so closely that encounters between them become plausible, even likely over cosmic timescales. Planetary systems in this region would experience frequent gravitational disruptions, their orbits perturbed by passing stars. Radiation levels surge as well, the combined light output from millions of closely packed stars creating a background glow thousands of times brighter than the feeble illumination we receive from distant stellar populations. At the very centre, radio and infrared observations reveal a compact source called Sagittarius A star, pronounced Sagittarius A star. This object radiates powerfully across the electromagnetic spectrum, despite occupying a region smaller than Mercury's orbit around the Sun. Its gravitational influence on nearby stars provides the most compelling evidence that it represents a supermassive black hole, a gravitationally collapsed region containing roughly 4 million times the Sun's mass, compressed into a volume no larger than a few light-hours across. Astronomers tracked individual stars orbiting this central object for more than 2 decades, measuring their positions with exquisite precision using infrared telescopes that peer through the obscuring dust. One star, designated S2, follows an elliptical path that brings it within 17 light-hours of Sagittarius A star at closest approach, roughly 4 times the distance from the Sun to Neptune. At this point in its orbit, S2 moves at nearly 3% of light speed, fast enough to complete one circuit around the black hole in just 16 years. The star's motion matches predictions from general relativity with extraordinary accuracy, confirming both the black hole's mass and its compact size. No other explanation fits the observations. Only a black hole can pack millions of solar masses into such a small volume without collapsing further or radiating away its energy. Nearly every large galaxy studied contains a supermassive black hole at its centre. These objects range from millions to tens of billions of solar masses, their size apparently correlated with the galaxy's total stellar mass and the velocity dispersion of stars in its core. This relationship suggests that black hole growth and galaxy formation are intimately connected, each influencing the other through mechanisms still being investigated. When material falls toward a supermassive black hole, friction and gravitational compression heat it to millions of degrees, causing it to radiate intensely before crossing the event horizon. In some galaxies, this accretion process becomes so energetic that the central region outshines all the galaxy's stars combined, creating what astronomers call an active galactic nucleus, or quasar. These objects, common in the early universe but rare today, can be detected across billions of light years, their prodigious energy output making them among the brightest persistent sources in the cosmos. The Milky Way's black hole currently sits in a quiet state, accreting material at a slow trickle rather than the torrent that powers active nuclei. Observations suggest it consumes only about 1 Earth mass of material per year, far below its theoretical maximum. This quiescence may be temporary. Every few thousand years, a star or gas cloud may wander too close, torn apart by tidal forces and fed into the black hole in a sudden burst of activity. For a few months or years, the galactic centre would blaze across multiple wavelengths, visible even through the obscuring dust. Then, as quickly as it began, the outburst would fade as the available fuel depleted. Whether such events pose any danger to life in the galaxy depends on distance. 26,000 light-years provide substantial protection. The radiation and particle flux from even a major outburst would diminish to harmless levels by the time it reached the Sun's neighbourhood, spread thin by the inverse square law that governs how energy disperses across space. Beyond the galactic centre, on the opposite side of the disk from our position, lie stars we will never observe in any detail. Dust lanes running through the galactic plane absorb visible and ultraviolet light, rendering distant disk regions opaque. Infrared and radio waves penetrate more effectively, allowing astronomers to map the galaxy's far side and measure the distribution of stars and gas. But individual stars remain invisible, their light scattered and absorbed before reaching our telescopes. The Milky Way contains an estimated 200 to 400 billion stars, though uncertainty in this figure remains large. Many stars are too faint to detect individually, even with our most powerful instruments. Others hide behind dust clouds or blend together in crowded fields near the galactic centre. Statistical methods based on stellar populations and mass estimates provide the best current counts, but future surveys will undoubtedly revise these numbers as techniques improve. The galaxy's total mass exceeds the sum of its visible stars by a factor of at least 10. This discrepancy first became apparent in the 1930s, when astronomer Fritz Zwicky measured the velocities of galaxies in the Coma cluster and found them moving too rapidly to remain gravitationally bound, unless far more mass existed than visible matter could account for. Similar measurements in the 1970s, particularly Vera Rubin's work on galactic rotation curves, confirmed that galaxies spin too fast for their visible matter alone to hold them together. Stars in the outer regions of spiral galaxies orbit at speeds that should fling them into intergalactic space, unless additional mass, undetected and unseen, provides extra gravitational pull. This dark matter, as it came to be called, apparently surrounds galaxies in vast halos extending far beyond the visible disk. Its nature remains one of the central mysteries in modern astrophysics. It does not emit, absorb, or reflect electromagnetic radiation at any wavelength. It interacts with ordinary matter only through gravity. Proposed candidates range from exotic subatomic particles to primordial black holes formed in the first seconds after the Big Bang. But despite decades of increasingly sensitive experiments, no dark matter particle has been conclusively detected. The presence of dark matter reshapes our understanding of cosmic scale in profound ways. When we observe the Milky Way's luminous disk stretching 100,000 light-years across, we're seeing only the visible component of a much larger structure. The dark matter halo extends perhaps 300,000 light-years from the galactic center, possibly farther, creating a roughly spherical cloud within which the visible galaxy sits embedded like a yolk within an egg. This invisible mass dominates the galaxy's gravitational field at large distances, controlling the orbits of satellite galaxies and globular clusters that circle far beyond the visible disk. The Magellanic Clouds, two irregular dwarf galaxies visible from Earth's southern hemisphere, orbit the Milky Way at distances of roughly 160,000 and 200,000 light-years. Their motions trace the dark matter halo's gravitational influence, allowing astronomers to estimate its total mass and distribution, even though the dark matter itself remains undetectable, except through its gravitational effects. Other galaxies populate the space around the Milky Way, forming what astronomers call the local group. This gravitationally bound collection contains more than 80 known members, though most are dwarf galaxies containing only millions to billions of stars rather than the hundreds of billions found in large spirals. Andromeda, designated M31 in astronomical catalogues, dominates the local group along with the Milky Way. Located roughly 2.5 million light-years away, Andromeda spans a similar diameter to our galaxy and contains perhaps 1 trillion stars, making it slightly more massive than the Milky Way, though recent measurements suggest the difference may be smaller than once thought. On a clear night far from city lights, Andromeda appears as a faint smudge to the naked eye, its light dimmed by distance and spread across an area several times the width of the full moon. Telescopic views reveal spiral structure similar to the Milky Way's, though seen from outside rather than from within. The light we observe from Andromeda departed that galaxy 2.5 million years ago, when Earth's climate was shifting toward the Ice Ages, and early human ancestors were just beginning to fashion stone tools. The photons travelled through intergalactic space for all that time, crossing the gulf between galaxies while our planet underwent dramatic transformations. When those photons began their journey, Andromeda was farther away than it is now. The galaxy approaches the Milky Way at roughly 110 kilometers per second, drawn by mutual gravitational attraction. In approximately 4 to 5 billion years, the two galaxies will collide, though this event will not resemble a physical crash. Stars within galaxies are so widely separated that direct collisions between them remain improbable even when galaxies merge. Instead, the two systems will pass through one another, their stars intermixing while gravitational interactions reshape both galaxies. Spiral structures will dissolve, stars will be flung onto new orbits, some ejected into intergalactic space, while others fall toward the merging cores. Over hundreds of millions of years, the two galaxies will collapse into a single elliptical galaxy, their ordered spiral patterns replaced by a roughly spherical swarm of stars following chaotic orbits. The local group occupies a volume roughly 10 million light-years across, though defining precise boundaries proves difficult since galaxies at the edges may be falling toward the Milky Way and Andromeda, or may belong to neighbouring groups instead. Beyond this region, other galaxy groups and clusters populate space in an increasingly regular pattern. The nearest large cluster, the Virgo cluster, lies approximately 54 million light-years away and contains over 2,000 galaxies. Its gravitational influence extends across tens of millions of light-years, pulling the local group and other nearby structures toward its centre at several hundred kilometers per second. This motion adds to the expansion of space, creating a complex pattern of velocities where local gravitational attraction partially counteracts the universal expansion, discovered in the 1920s. That discovery emerged from observations of galaxy spectra, the rainbow patterns produced when light disperses through a prism or diffraction grating. Each chemical element absorbs and emits light at specific wavelengths, determined by the energy levels of electrons orbiting its nucleus. These spectral lines act as fingerprints, allowing astronomers to identify elements present in distant objects and measure their physical conditions. When Edwin Hubble and Milton Humason examined spectra from distant galaxies in the late 1920s, they found something unexpected. The spectral lines appeared shifted toward longer, redder wavelengths compared to laboratory measurements of the same elements. Moreover, the size of this redshift correlated with distance. Galaxies farther away showed larger redshifts, their light stretched by a factor that increased roughly proportionally with their separation from the Milky Way. Several interpretations of this redshift seemed plausible initially. Light travelling through space might lose energy over time, shifting toward longer wavelength through some unknown interaction with the vacuum. This tired light hypothesis fell out of favour as it failed to explain other observed properties of distant galaxies. Alternatively, galaxies might be moving away from us through space, their motion creating a Doppler shift similar to how a receding ambulance siren drops in pitch. This explanation worked better, but raised troubling questions about why galaxies would flee preferentially from the Milky Way, suggesting an implausibly special position for our galaxy in the cosmic order. The correct interpretation, proposed by Georges Lemaitre in 1927 and later confirmed by Hubble's observations, involved neither energy loss nor motion through space in the conventional sense. Instead, space itself expands, carrying galaxies apart as it stretches. The light travelling through this expanding space stretches along with it, arriving at Earth with longer wavelengths than when it departed. This expansion does not occur within galaxies or galaxy clusters, where gravitational binding holds structures together against the cosmic expansion. The Milky Way and Andromeda are not expanding, nor are the atoms in your body spreading apart. Expansion operates only at scales where gravity's influence becomes negligible, primarily in the vast regions between galaxy clusters. At these scales, space itself grows, inserting new distance between objects without moving them through any pre-existing space. This concept challenges intuition because everyday experience provides no parallel. Objects move through space in our world. Space itself remains a passive stage on which motion occurs. But general relativity, the theory that best describes gravity and space-time structure, allows for dynamic space that can stretch, compress, or curve in response to matter and energy. The rate of this expansion, called the Hubble constant, indicates how rapidly distance grows between widely separated objects. Current measurements place it near 70 kilometers per second per megaparsec, though different measurement techniques yield slightly different values, and this discrepancy remains an active area of research. A megaparsec equals roughly 3.26 million light-years, so two galaxies separated by this distance recede from one another at 70 kilometers per second, due solely to cosmic expansion. Double the separation and the recession velocity doubles as well. At 10 megaparsecs, expansion carries galaxies apart at 700 kilometers per second. At 100 megaparsecs, 7,000 kilometers per second, or about 2% of light speed. This proportional relationship means that sufficiently distant galaxies recede faster than light speed, not because they move through space at such velocities, but because the accumulated expansion of space between us and them exceeds light's pace. This reality creates a fundamental horizon in our observations. Light from galaxies receding faster than light speed can never reach us, no matter how long we wait. The expansion of space carries these objects away more rapidly than their light can traverse the growing distance. Objects beyond this cosmological horizon remain forever invisible, not because they are intrinsically dark or obscured, but because the geometry of expanding spacetime prevents their light from ever completing the journey to Earth. The position of this horizon depends on the expansion rate and how that rate has changed over cosmic history. Current estimates place it roughly 46 billion light-years away, though this figure requires careful interpretation. The universe is approximately 13.8 billion years old, meaning we might naively expect to see only objects within 13.8 billion light-years. But space has been expanding during the time light travelled toward us, so objects whose light has taken 13.8 billion years to arrive now sit much farther away than that travel time suggests. The most distant objects we observe appear as they existed in the universe's first billion years, when the first stars and galaxies were just forming. Their light has travelled for more than 13 billion years to reach our telescopes, stretched by cosmic expansion until visible wavelengths shift into the infrared portion of the spectrum. These early galaxies look smaller and more irregular than mature spirals like the Milky Way, with bursts of star formation creating pockets of brilliant blue light surrounded by darker regions still accumulating gas. Some contain supermassive black holes, already weighing billions of solar masses despite forming less than a billion years after the Big Bang. a puzzling observation that challenges models of how such objects grow. The precise mechanisms that assembled the first galaxies remain incompletely understood, though simulations combining gravity, gas dynamics, and dark matter evolution reproduce many observed properties. Between these distant galaxies and our own lies, a vast volume containing hundreds of billions of other galaxies, each a collection of millions to trillions of stars separated from its neighbours by typically millions of light years. Astronomers have catalogued millions of these systems, mapping their positions, measuring their distances, and classifying their types. Spiral galaxies like the Milky Way and Andromeda possess rotating disks with spiral arm patterns and ongoing star formation. Elliptical galaxies contain older stellar populations arranged in roughly spherical or ellipsoidal shapes, with little gas remaining to fuel new star birth. Irregular galaxies lack clear structural patterns, their stars distributed chaotically, often as a result of gravitational interactions with neighbours. Beyond individual galaxies, larger patterns emerge. Galaxies cluster together in groups and clusters, which themselves align along filaments and sheets, separated by enormous voids containing few galaxies. These structures trace the distribution of dark matter, which provides the gravitational framework along which ordinary matter accumulates. In the early universe, dark matter began clumping under its own gravity, creating wells of gravitational potential. Ordinary matter, composed of protons, neutrons, and electrons, fell into these wells, compressed and heated until stars ignited. The largest concentrations of dark matter became the sites of galaxy clusters, collections containing hundreds to thousands of galaxies bound together by their mutual gravity. The Coma cluster, where Fritz Zwicky first found evidence for dark matter, contains over 1,000 identified galaxies and likely many more too faint to detect individually. Its total mass exceeds 10 to the 15th solar masses, most of it in the form of dark matter spread throughout the cluster volume. X-ray observations reveal clouds of hot gas filling the space between galaxies, heated to tens of millions of degrees by gravitational compression as the cluster formed. This gas contains more ordinary matter than all the cluster's stars combined, yet it still represents only about 15% of the total mass, with dark matter accounting for the remainder. Galaxy clusters themselves cluster into superclusters, loose associations spanning hundreds of millions of light years. The local group belongs to the Virgo supercluster, a concentration of galaxies and galaxy groups centered on the Virgo cluster. Recent mapping efforts have revealed an even larger structure called Laniakea, a supercluster complex containing roughly 100,000 galaxies including our own. This structure spans 520 million light years and contains approximately 10 to the 17th solar masses worth of material. Galaxies within Laniakea move toward a central point called the Great Attractor, drawn by the combined gravitational pull of countless mass concentrations in that region. But even Laniakea does not represent the largest scale of cosmic structure. Surveys mapping millions of galaxies reveal that superclusters align along filaments separated by voids, creating a cosmic web pattern reminiscent of soap bubbles or biological cell structures. These voids represent some of the most empty regions in the universe. A typical void spans 100 to 400 million light-years across and contains very few galaxies, perhaps a handful of small dwarf systems compared to the thousands found in an equivalent volume within a supercluster. The space inside voids is not perfectly empty. Diffuse gas exists there, and dark matter presumably fills these regions as it does everywhere else. But the density drops far below cosmic average, making voids the closest the universe comes to true emptiness. Some voids appear completely devoid of luminous galaxies across their entire volume, though gravitational lensing studies suggest dark matter filaments may thread through them, invisible bridges connecting the denser regions that surround each void. The cosmic web structure emerged naturally from tiny density fluctuations present in the early universe. When the cosmos was only a few 100,000 years old, it existed as a hot, nearly uniform plasma of ionized hydrogen and helium mixed with dark matter. Temperature variations across this plasma amounted to only about 1 part in 100,000, tiny ripples in an otherwise smooth sea. But these ripples carried crucial information about the universe's composition, expansion rate, and geometry. As the universe expanded and cooled, gravity amplified the density variations. Regions slightly denser than average attracted more matter, growing denser still. Regions slightly less dense lost matter to their denser neighbours, becoming increasingly empty. Over hundreds of millions of years, this process generated the pattern we observe today. Dense filaments and sheets surrounding empty voids, with galaxy clusters marking the nodes where multiple filaments intersect. We can observe these early density fluctuations directly by studying the cosmic microwave background, radiation released when the universe first became transparent to light. Before that moment, approximately 380,000 years after the Big Bang, the universe was hot enough that electrons remained free rather than bound into atoms. Free electrons scatter photons efficiently, making the early cosmos opaque much as fog obscures vision. As expansion cooled the universe below about 3000 degrees Kelvin, electrons combined with protons to form neutral hydrogen atoms. Photons could then travel freely, no longer scattered by every interaction with free electrons. The light released at this moment has been travelling through space ever since, stretched by cosmic expansion from visible wavelengths into the microwave portion of the spectrum. This cosmic microwave background radiation reaches Earth from all directions, a faint glow with a temperature of approximately 2.7 degrees above absolute zero. Satellites equipped with sensitive microwave detectors have mapped this radiation across the entire sky, measuring its temperature to within millionths of a degree. The resulting maps reveal a remarkably uniform signal with tiny variations imprinted on it, the fossilized remnants of those density fluctuations that would later grow into galaxies and clusters. Hotspots in the microwave background, regions where the temperature exceeds the average by a few hundred millionths of a degree, correspond to areas that were slightly denser when the radiation was released. Cold spots mark regions that were slightly less dense. These temperature differences translate directly into density variations because denser regions had stronger gravitational fields, and photons climbing out of those fields lost energy and cooled through a process called gravitational redshift. The pattern of hot and cold spots contains statistical information about the universe's properties at the moment of photon release. The typical angular size of these spots, roughly 1 degree across, reflects the distance sound waves could travel through the primordial plasma before atoms formed and pressure support vanished. By measuring this characteristic scale and comparing it to theoretical predictions, cosmologists can determine fundamental parameters like the universe's geometry, its expansion rate at early times, and the relative amounts of ordinary matter, and dark energy. These measurements constrain competing cosmological models with remarkable precision. The universe appears spatially flat on large scales, meaning parallel lines remain parallel rather than eventually converging or diverging as they would in curved geometries. The photons comprising this background radiation have been travelling for approximately 13.8 billion years. They represent the oldest light we can possibly observe, released when the universe was less than 1/400th its current age. No electromagnetic signal from earlier times can reach us because the universe was opaque before atoms formed. Any light produced in that era scattered countless times before photon release. Its directional information scrambled beyond recovery. The cosmic microwave background thus represents a fundamental observational limit, an informational horizon beyond which electromagnetic observations cannot penetrate. Some proposals suggest detecting gravitational waves or neutrinos from even earlier epochs, since these signals can travel through the opaque early universe, but such observations remain far beyond current technical capability. The microwave background photons we detect today were emitted from a spherical shell surrounding Earth, the set of points from which light takes exactly 13.8 billion years to reach us. We sit at the centre of this shell, not because of any special cosmic position, but simply because we define the shell by reference to our own location. An observer in Andromeda would see a similar background, centred on themselves, with the same statistical properties but different detailed patterns. The radius of this shell equals the distance light can travel in 13.8 billion years through an expanding universe, which works out to roughly 46 billion light-years, accounting for expansion during the light's journey. This defines the radius of the observable universe, the spherical volume within which events can potentially affect us or be observed by us. Beyond this observable region, the universe presumably continues. No evidence suggests it ends at the boundary we observe. the microwave background appears statistically uniform across the entire sky, showing no sign of an edge or wall. The simplest interpretation holds that similar structures, more galaxies and clusters and voids, extend beyond what we can see, but confirming this directly is impossible. Light from those regions has not had time to reach Earth since the Big Bang, and in an accelerating expansion, it never will. The observable universe represents not the totality of existence, but merely the fraction accessible to observation from our location and time. Some theoretical models suggest the universe may be far larger than the observable region, perhaps even infinite in extent. If the universe is spatially flat and extends without boundary, then infinite volume follows naturally. An infinite universe need not have an infinite amount of matter, since density could drop to zero at large distances, but current evidence suggests matter density remains roughly constant at the larger scales we can measure. If that uniformity extends beyond the observable horizon, the total universe contains infinitely many galaxies, infinitely many stars, and eventually infinitely many planets. Probability theory in infinite spaces leads to strange conclusions. Any event with non-zero probability, no matter how small, occurs infinitely many times. Somewhere beyond our observable horizon, another planet orbits another sun-like star, with continents and oceans arranged identically to Earth's. The probability of such an exact duplication is incomprehensibly tiny but non-zero, which in an infinite universe guarantees infinite replicas. These philosophical puzzles aside, the observable universe alone provides ample scope to consider scale. Current surveys have catalogued approximately 200 billion to 2 trillion galaxies within the observable volume, though this estimate carries large uncertainty. Early surveys detected only the brightest galaxies, missing fainter dwarf systems and distant objects too dim to register against the sky background. Deeper observations with more sensitive instruments continue revealing previously unseen populations, pushing the total count upward. Each of these galaxies contains millions or trillions of stars. Taking a conservative average of 100 billion stars per galaxy, and assuming 200 billion galaxies yields a total of approximately 10 to the 22nd stars in the observable universe, a number so large it exceeds the grains of sand on all Earth's beaches combined by perhaps a millionfold. Most of these stars host planetary systems. Data from exoplanet surveys over the past 3 decades indicate that planets are the rule rather than the exception. The Kepler Space Telescope, which monitored over 150,000 stars for evidence of transiting planets, found that roughly half of Sun-like stars host at least one planet. Extrapolating to all stellar types and accounting for selection biases suggests there may be trillions of planets in the Milky Way alone. Some orbit too close to their stars, baked to temperatures where surface rock melts. Others circle at extreme distances where temperatures plunge hundreds of degrees below zero, but a fraction inhabit temperate zones where liquid water could exist on a planetary surface, the basic requirement for life as we understand it. Estimates of potentially habitable planets in our galaxy alone range from billions to tens of billions, depending on which criteria define habitability and how many planets meet those standards. Multiply these billions of potentially habitable worlds by the hundreds of billions of galaxies in the observable universe, and the total number of locations where life might arise becomes astronomically large. Yet we have detected no confirmed evidence of life beyond Earth. No radio signals bearing the signature of intelligent origin. No optical beacons flashing mathematical sequences. No obvious signs of planetary engineering or energy harvesting at stellar scales. This absence, sometimes called the Fermi paradox after physicist Enrico Fermi, who reportedly posed the question during a lunch conversation, admits multiple interpretations. Perhaps life emerges rarely despite favourable conditions. Perhaps intelligence or technological civilization represents an unlikely evolutionary outcome even when life exists. Perhaps civilizations destroy themselves shortly after developing technology capable of interstellar communication. Or perhaps the galaxy teems with life and intelligence, but the distances between inhabited worlds remain so vast that contact has not yet occurred, or is not occurring in ways we can detect. The distances between stars impose severe constraints on any civilization attempting interstellar communication or travel. Even at light speed, signals take years or centuries to traverse the gaps between neighbouring systems. Physical travel faces even steeper challenges. Accelerating a spacecraft to relativistic velocities requires enormous energy, and the faster the craft moves, the more energy is needed for further acceleration. At 90% of the light speed, relativistic effects become significant. Time aboard the spacecraft passes more slowly relative to stationary observers, allowing travelers to subjectively experience shorter journey times than the actual elapsed years. But from Earth's reference frame, decades or centuries pass for even nearby destinations. The travelers return, if they return at all, to find everyone they knew long dead and their civilization transformed or vanished. These limitations suggest that if intelligent life exists elsewhere, direct contact between civilizations separated by thousands of light years remains implausible with any technology we can currently envision. Radio communication offers a more feasible alternative, but even this faces challenges. The inverse square law dictates that signal strength diminishes with the square of distance. A transmission detectable across 10 light years requires 100 times more power to reach 100 light years, 10,000 times more for 1,000 light years. Background noise from natural sources, cosmic rays, thermal radiation from the interstellar medium, and interference from terrestrial transmitters all degrade signal quality. Detecting a faint artificial signal amid this noise requires enormous antenna arrays and sophisticated signal processing, resources that only recently became available to human civilization. Our own transmissions have been leaking into space for roughly a century, since the invention of radio broadcasting. These signals propagate outward at light speed, creating an expanding bubble of electromagnetic noise centered on Earth. The bubble currently extends approximately 100 light-years in radius, encompassing several thousand star systems. But by the time these signals reach even the nearest stars, they have weakened to barely detectable levels, competing with radiation from the sun and other natural sources. Most early transmissions from analog radio and television broadcasts used omnidirectional antennas that scattered power across the entire sky. Modern communications increasingly rely on directional antennas, fiber optics, and satellites, technologies that leak less radiation into space. Our planet's radio signature may already be fading from its peak decades ago, visible to hypothetical distant observers only as a brief, century-long flare in an otherwise quiet planetary spectrum. The absence of detected extraterrestrial signals may simply reflect the limited duration of our search. Systematic efforts to monitor the sky for artificial radio emissions began in earnest only in the 1960s, giving us fewer than 70 years of serious observation. During this time, only a tiny fraction of possible target stars have been examined, and those observations covered limited frequency ranges and durations. A distant civilization could be transmitting continuously, but if we point our receivers at the wrong star, or listen at the wrong frequency, or observe during a gap in their transmission schedule, we detect nothing. The search space remains vast. Billions of potential target stars, each potentially transmitting at any of billions of possible frequencies at any time over the past several billion years of galactic history. Scale plays a central role in this search. If civilizations arise rarely, separated on average by thousands of light years, then the probability of detecting one from Earth remains low despite the billions of potential host stars. If they arise more commonly, but persist only briefly before extinction or cultural transformation ends their transmitting phase, then only a small number exist at any given time, further reducing detection odds. Conversely, if long-lived civilizations are common and actively attempt to communicate across interstellar distances, then our failure to detect them suggests either that we are searching incorrectly, looking in the wrong places or at the wrong frequencies, or that some unknown factor suppresses the emergence of intelligence or technology throughout the galaxy. Each possibility carries implications for humanity's long-term future and our place within the cosmic order. The structure of the observable universe extends beyond galaxies and clusters to encompass scales where individual objects become indistinguishable, blurring into a uniform distribution of matter and energy. At the largest scales cosmologists can measure, roughly 1 billion light-years and above, the universe appears statistically homogeneous. Any sufficiently large volume contains approximately the same number of galaxies, the same average density of matter, and the same mixture of galaxy types. This uniformity suggests that the fundamental properties of space and physical law do not vary with position. The laws governing gravity, electromagnetic forces, and nuclear interactions appear identical across the entire observable volume, giving us confidence that observations of distant galaxies tell us about physics rather than merely local phenomena. This large-scale uniformity contrasts sharply with the dramatic variations apparent at smaller scales. Within a galaxy, matter concentrates into stars, planets, and interstellar clouds, creating density variations of factors of millions or billions compared to intergalactic space. Between galaxies, density drops precipitously in the voids while rising in the filaments and clusters, but average these variations over large enough volumes, and they wash out into a smooth background. Cosmologists describe this property as the cosmological principle, the assumption that the universe looks roughly the same from any vantage point when viewed at sufficiently large scales. No location occupies a special position. No direction appears fundamentally different from any other. This principle guided the development of modern cosmology and underpins most theoretical models of cosmic evolution. Yet the uniformity observed at these scales demands explanation. Why should regions of space separated by billions of light-years, which have never been in causal contact since the Big Bang, exhibit identical properties? Light from one side of the observable universe has not had time to reach the other side, meaning no physical process operating at or below light speed could have synchronized conditions across such distances. This horizon problem troubled cosmologists for decades until the development of inflationary theory in the 1980s. Inflation proposes that the universe underwent a brief period of exponential expansion in its first tiny fraction of a second, growing from subatomic size to perhaps grapefruit size in roughly 10 to the negative 35 seconds. This rapid expansion stretched a small, causally connected region to enormous size, creating the uniformity we observe today. Regions that appear causally disconnected now were once in contact before inflation drove them apart. Inflationary theory solves several puzzles beyond the horizon problem. It explains why the universe appears spatially flat, despite the fact that any small deviation from perfect flatness grows rapidly over time. Inflation stretches space so dramatically that any initial curvature becomes negligible, like inflating a balloon until its surface appears flat to an ant walking on it. The theory also accounts for the small density fluctuations visible in the cosmic microwave background. Quantum fluctuations, tiny random variations in energy density at subatomic scales, existed in the pre-inflationary universe. Inflation amplified these quantum jitters to cosmic size, converting microscopic irregularities into the macroscopic density variations that seeded galaxy formation. Precise measurements of the microwave background's fluctuation pattern match predictions from inflationary models with remarkable accuracy, providing strong support for the theory despite the fact that the inflationary epoch itself remains beyond direct observational access. If inflation occurred, the observable universe represents only a minute fraction of the total inflated volume. The region that underwent exponential expansion likely extends trillions upon trillions of light-years beyond what we can see, possibly infinitely far if inflation never completely stopped. Some versions of inflationary theory suggest the process continues in regions outside our observable patch, creating a perpetually inflating multiverse where pocket universes nucleate like bubbles in boiling water. Each pocket experiences its own local physics, its own values for fundamental constants, perhaps even its own number of spatial dimensions. Our observable universe would be one bubble among countless others, each isolated from its neighbours by inflating space that expands faster than light can traverse it. These speculations push cosmology into territory where observational confirmation becomes challenging or impossible. If other bubble universes exist beyond our cosmic horizon, we cannot observe them directly. Some theorists propose that collisions between bubbles might leave detectable imprints in the cosmic microwave background, circular patterns of slight temperature variations marking where another universe brushed against ours during inflation. Searches for such signatures have found no convincing candidates, though the statistical significance remains debatable. Without direct evidence, the multiverse remains a theoretical possibility rather than an established feature of reality. Its consideration serves mainly to illustrate how far our understanding of cosmic scale has pushed beyond the directly observable, into realms where mathematics and physical theory guide exploration more than telescopic data. Returning to what we can observe directly, The scale of structures within the universe follows patterns determined by the interplay between gravity, dark matter, and dark energy. Gravity pulls matter together, attempting to create ever larger bound structures. Dark matter provides most of the gravitational influence, forming potential wells into which ordinary matter falls. But dark energy, a mysterious component comprising roughly 68% of the universe's total energy density, opposes this collapse at the larger scales. Dark energy acts as a kind of anti-gravity, not repelling matter directly but causing space itself to expand at an accelerating rate. This acceleration, discovered in 1998 through observations of distant supernovae, represents one of the most surprising findings in modern cosmology. Type Ia supernovae, stellar explosions that occur when white dwarf stars accumulate too much mass and collapse, provide standardized candles for measuring cosmic distances. These events reach predictable peak brightness, allowing astronomers to determine how far away they occurred by comparing observed brightness to the known intrinsic luminosity. When researchers measured distances to dozens of these supernovae in distant galaxies and compared those distances to the galaxy's redshifts, they found a mismatch. The supernovae appeared fainter than expected, indicating they were farther away than a constant expansion rate would predict. The only explanation consistent with general relativity involved an accelerating expansion, driven by some form of energy permeating all of space. Dark energy differs fundamentally from any familiar substance. It does not clump into structures like ordinary matter or dark matter. Its density remains constant as space expands, meaning that as the universe grows, the total amount of dark energy increases proportionally with volume. This property distinguishes it from matter and radiation, which become more dilute as space expands. The simplest theoretical candidate for dark energy is the cosmological constant, a term Albert Einstein introduced into his equations of general relativity, and later called his greatest blunder. Einstein added this term to allow static universe solutions, counterbalancing gravity's tendency to cause collapse. When observations revealed the universe was expanding, he abandoned the cosmological constant as unnecessary. But the accelerating expansion discovered decades later requires exactly such a term, though with a value far smaller than Einstein originally considered. The cosmological constant can be interpreted as the energy density of empty space itself, the vacuum energy that quantum field theory predicts should exist everywhere. Quantum mechanics treats empty space not as truly empty, but as filled with virtual particles that constantly appear and disappear, borrowing energy from the vacuum for brief instants allowed by Heisenberg's uncertainty principle. Calculating the energy density these virtual particles should produce yields predictions that exceed observed dark energy density by roughly 120 orders of magnitude, the worst prediction in the history of physics. This spectacular failure indicates something fundamentally wrong with our understanding of either quantum field theory, gravity, or both. Resolving this cosmological constant problem remains one of theoretical physics' central challenges. Regardless of its physical nature, dark energy's influence on cosmic structure becomes dominant at scales of hundreds of millions of light-years and above. At smaller scales, gravitational attraction within galaxy clusters and superclusters overwhelms dark energy's repulsive effect, allowing structures to remain bound. But at larger scales, dark energy dominates, preventing matter from collapsing into progressively larger structures. The cosmic web of filaments and voids represents the largest scale at which gravity has successfully assembled matter against expansion. No structures larger than superclusters exist because dark energy, combined with the finite age of the universe, has prevented gravity from pulling together more distant concentrations of matter. The acceleration driven by dark energy has profound implications for the universe's far future. Galaxies not already bound to the local group or other gravitationally connected structures will recede beyond the cosmic horizon, their light redshifted to undetectability as accelerating expansion carries them away. In trillions of years, an observer in the Milky Way, or whatever galaxy forms from the Milky Way and Andromeda's eventual merger, will see only the galaxies in their immediate group. The rest of the observable universe will have disappeared beyond the horizon, faded to darkness. The cosmic microwave background will cool to temperatures indistinguishable from absolute zero. Stars will exhaust their fuel, leaving behind white dwarfs, neutron stars, and black holes. Eventually, Even these remnants will evaporate through quantum processes, though the timescales involved exceed 10 to the 100 years, a duration so vast that the current age of the universe represents barely a flicker in comparison. These extreme timescales illustrate how cosmic scale encompasses not only spatial dimensions, but temporal ones as well. The universe's age of 13.8 billion years seems immense by human standards, but it represents only a brief moment in the full sweep of cosmic time. Stars will continue forming for trillions of years as long as hydrogen and helium remain available in sufficient quantities. The smallest red dwarf stars, burning their fuel with miserly efficiency, will shine for 10 trillion years or more before exhausting their supply. By comparison, the Sun's remaining lifetime of approximately 5 billion years seems almost brief. When the last star finally winks out, the universe will enter an era lasting perhaps 10 to the 40 years during which stellar remnants dominate the cosmos. Black holes will persist even longer, evaporating through Hawking radiation on timescales that scale with their mass. A solar mass black hole requires 10 to the 67 years to evaporate completely. Supermassive black holes weighing billions of solar masses endure for 10 to the 100 years before finally dissolving into quantum radiation. After the black holes evaporate, only elementary particles remain, scattered across a volume expanding without limit. Photons stretch to wavelengths larger than the observable universe. Electrons and positrons drift through the void separated by distances incomprehensibly vast. The temperature approaches absolute zero asymptotically, never quite reaching it, but falling to levels where thermal energy becomes negligible. In this heat death scenario, no usable energy remains, no gradients exist to drive processes or sustain complexity. The universe continues existing but achieves maximum entropy, a state of perfect uniformity where nothing further can happen. Whether this fate actually awaits depends on dark energy's long-term behaviour, which remains uncertain. If dark energy strengthens over time rather than remaining constant, expansion could accelerate catastrophically, eventually tearing apart galaxies, stars, planets, and even atoms in a Big Rip scenario. If dark energy decays or reverses, expansion might slow or even reverse into contraction, leading to a big crunch. Current observations suggest dark energy's density remains remarkably constant, consistent with a true cosmological constant, but the measurements cover only the last several billion years of cosmic history. Extrapolating this behaviour trillions of years into the future requires assumptions that may not hold. The ultimate fate of the universe remains an open question, one that may be genuinely unknowable given the fundamental limits on how far we can observe and how long we can measure. Yet the question itself illustrates how cosmic scale forces us to contemplate spans of time that render human experience, even human history, effectively instantaneous. Our species has existed for perhaps 300,000 years, recorded history spans roughly 10,000 years, and scientific cosmology itself emerged only within the last century. We are attempting to understand processes operating over timescales a trillion times longer than our entire existence as a species. The spatial scales involve present similar challenges to intuition. The smallest distances physics can meaningfully describe approach the Planck length, approximately 10 to the negative 35 meters. At this scale, quantum fluctuations in space-time geometry become so violent that conventional notions of distance lose meaning. Space itself may become grainy or foamy, with the smooth continuum we experience at larger scales breaking down into discrete quanta. String theory and other quantum gravity proposals suggest additional spatial dimensions may exist at these scales, curled up so tightly they remain invisible to experiments conducted at accessible energies. These compactified dimensions might measure only a few Planck lengths across, creating geometric structures completely hidden from direct observation, but potentially influencing fundamental particle properties through their topology. Moving upward from the Planck scale, we encounter the realm of elementary particles. Quarks and electrons, the constituents of atoms, have no known internal structure and may be truly point-like. Their measured size, meaning the scale at which their behaviour deviates from point particle predictions, remains below 10 to the negative 18 meters, the limit of current experimental resolution. Protons and neutrons, composed of 3 quarks, each bound by the strong nuclear force, measure approximately 10 to the negative 15 meters across. Atomic nuclei range from roughly the same size for hydrogen to about 10 to the negative 14 meters for the larger stable elements. The atoms themselves, with their electron clouds, span 10 to the negative 10 meters, about 1 angstrom. This scale defines chemistry and molecular biology, the distances at which electromagnetic forces between atoms create bonds and determine material properties. Molecules built from these atoms range from simple diatomic structures like hydrogen or oxygen to massive biological polymers containing millions of atoms. DNA molecules in human cells, if stretched end to end, would measure roughly 2 meters long but only 2 nanometers wide, a ratio of 1,000,000,000 to 1. Proteins fold into complex three-dimensional shapes determined by sequences of amino acids, creating molecular machines that catalyze reactions, transport materials, and respond to signals. Viruses sitting at the boundary between living and non-living measure tens to hundreds of nanometers across. Bacteria, the simplest truly independent organisms, range from about 1 micrometer for the smallest species to tens of micrometers for larger ones. Human cells vary from 7 micrometers for red blood cells to over 100 micrometers for some nerve cells, though most fall in the 10 to 30 micrometer range. These cellular scales bridge the gap between molecular structures too small to see with visible light and macroscopic objects visible to the naked eye. Human beings span roughly 1 to 2 meters in height, containing trillions of cells organized into tissues, organs, and integrated physiological systems. We exist at a scale roughly halfway between atoms and the Earth on a logarithmic scale, able to manipulate objects from millimeters to meters with natural ease, but requiring instruments to perceive anything smaller or grasp anything larger. This middle position may not be coincidental. Intelligent life requires complex chemistry, which functions optimally at scales from nanometers to micrometers. It also requires bodies large enough to support nervous systems with sufficient neurons for abstract thought, which implies sizes of centimeters to meters. Smaller organisms lack the neural capacity for complex cognition. Larger ones face challenges with structural support and resource distribution that may limit the emergence of intelligence through different evolutionary pathways. The Earth itself measures roughly 12,700 kilometers in diameter, large enough to retain an atmosphere and generate a protective magnetic field, but small enough that humans can comprehend its scale through direct experience. We can travel around the planet, view it from space, hold its entire geography in mental models built from maps and photographs. The Moon orbits at 384,000 kilometers, about 30 Earth diameters away, close enough that light takes only 1.3 seconds to traverse the gap. The Sun sits 150 million kilometers distant, far enough that its light requires 8 minutes and 20 seconds to arrive, but close enough that we receive sufficient illumination and warmth to sustain life. The spacing between planets follows a rough geometric progression, each orbit lying approximately 1.5 to 2 times farther from the Sun than the previous one, a pattern first noted by Johann Titius and Johann Bode in the 18th century. This Titius-Bode law lacks rigorous theoretical justification, but hints at dynamical processes during solar system formation that favoured particular orbital configurations. Mercury circles at 58 million kilometres, Venus at 108 million, Earth at 150 million, Mars at 228 million. The asteroid belt occupies a broad zone from roughly 300 to 500 million kilometres, a region where Jupiter's gravitational influence prevented a planet from coalescing. Jupiter itself orbits at 778 million kilometres, more than 5 times Earth's distance. Saturn lies nearly twice as far at 1.4 billion kilometres. Uranus reaches 2.9 billion kilometres. Neptune, the outermost major planet since Pluto's reclassification, circles at 4.5 billion kilometres, 30 times Earth's distance from the Sun. Beyond Neptune extends the Kuiper Belt, a disk of icy bodies including Pluto and thousands of smaller objects. This region spans from Neptune's orbit to roughly 50 astronomical units, or 7.5 billion kilometres. Still farther out lies the scattered disk, where objects follow highly elliptical orbits that carry them hundreds of astronomical units from the Sun at their most distant points. These distant objects take centuries or millennia to complete single orbits, their surfaces frozen to temperatures barely above absolute zero, never warmed by the faint sunlight that reaches those remote distances. Some astronomers propose that an undiscovered planet, sometimes called Planet 9, orbits in this region, its gravitational influence subtly affecting the orbits of smaller bodies. If such a planet exists, it might orbit at 200 to 1,000 astronomical units, taking 10,000 to 20,000 years per orbit. The heliosphere, the region dominated by the solar wind's influence, extends roughly 120 astronomical units before the interstellar medium's pressure balances the outward push of particles from the Sun. Voyager 1 crossed this boundary in 2012 at approximately 121 astronomical units, becoming the first human-made object to enter interstellar space. The probe continues transmitting data, though its instruments will likely fail within the next few years as their power sources decay. Even at 17 kilometers per second, Voyager moves slowly on cosmic scales, requiring 40,000 years to pass within 2 light-years of another star system. The Oort cloud, a hypothetical sphere of icy bodies surrounding the solar system, may extend from roughly 2,000 astronomical units to as far as 100,000 astronomical units, roughly halfway to Proxima Centauri. This structure, proposed by Dutch astronomer Jan Oort in 1950 to explain the origins of long-period comets, has never been directly observed. The objects composing it are too small and distant to detect with current telescopes, their existence inferred from the trajectories of comets that occasionally fall inward toward the Sun. If the Oort cloud exists as theorized, it contains trillions of icy bodies with a combined mass perhaps several times that of Earth, remnants from the solar system's formation scattered to enormous distances by gravitational encounters with the giant planets. This outermost boundary of the Sun's gravitational influence approaches the scale of interstellar distances, though still falling short by factors of several. The gap between solar systems represents a true threshold, a transition from regions dominated by individual stars to the collective gravitational environment of the galaxy. Interstellar space contains approximately 1 hydrogen atom per cubic centimetre, on average, though the distribution varies significantly. Dense molecular clouds may contain thousands or millions of atoms per cubic centimetre, while the hot gas between clouds drops to less than 1 atom per 100 cubic centimetres. Dust grains, microscopic particles of carbon, silicon and other elements scatter light and absorb ultraviolet radiation, creating the dark lanes visible in images of the Milky Way. Cosmic rays, high-energy particles accelerated to nearly light speed by supernova shockwaves and other violent processes, streak through interstellar space in all directions. These particles, mostly protons with a sprinkling of heavier nuclei and electrons, carry energies ranging from millions to trillions of electron volts. The most energetic cosmic rays exceed 10 to the 20 electron volts, energies incomprehensible in human terms. A single subatomic particle at this energy carries roughly the kinetic energy of a baseball thrown at moderate speed, compressed into a volume trillions of times smaller. Where and how nature accelerates particles to such extremes remains partially mysterious, though the most energetic events appear to originate from outside our galaxy, perhaps from the vicinity of supermassive black holes in active galactic nuclei or from colliding galaxy clusters. Magnetic fields thread through interstellar space, their strength typically measuring a few microgauss, roughly 1,000,000 times weaker than Earth's surface field. Despite this weakness, these fields influence the motion of charged particles and help shape the structure of molecular clouds where stars form. The fields align roughly with the spiral arms, their geometry reflecting the galaxy's rotation and the complex interplay of gravity, gas pressure, and magnetic tension. Measurements of starlight polarization, caused when light passes through aligned dust grains in magnetized clouds, map these invisible fields across portions of the galactic disk. Stars form in regions where interstellar gas accumulates densely enough that gravitational collapse overcomes thermal pressure and magnetic support. These molecular clouds, composed primarily of hydrogen molecules with traces of carbon monoxide, water, ammonia, and hundreds of other compounds, contain enough material to form thousands or millions of stars. The Orion Nebula, one of the nearest active star-forming regions at roughly 1,300 light-years, spans approximately 24 light-years across, and contains enough gas to make 2,000 solar masses worth of new stars. Young stars visible within the nebula, some only a few 100,000 years old, heat surrounding gas with their ultraviolet radiation, creating the glowing emission that makes the nebula visible to small telescopes and even naked eyes under dark skies. The stellar life cycle connects these formation regions to the dispersed atoms filling interstellar space. Stars like the Sun burn hydrogen into helium for billions of years before exhausting their core fuel and expanding into red giants. These bloated stars shed their outer layers through stellar winds and eventually eject most of their mass in a planetary nebula, leaving behind a white dwarf core. More massive stars follow a different path, fusing elements up through iron before their cores collapse catastrophically in supernova explosions. These events release more energy in a few seconds than the Sun emits over its entire 10 billion year lifetime, briefly outshining entire galaxies. The explosion hurls processed material into space at thousands of kilometers per second, enriching the interstellar medium with carbon, oxygen, silicon, iron, and heavier elements formed during the explosion itself. This chemical enrichment process plays a crucial role in cosmic evolution. The universe emerged from the Big Bang containing only hydrogen, helium, and trace amounts of lithium. Every heavier element, from the carbon in our bodies to the iron in Earth's core to the gold in jewelry, formed inside stars or during supernova explosions. Early generations of stars composed solely of primordial hydrogen and helium could not host planets like Earth. Rocky planets require silicon, oxygen, magnesium, and iron, elements that did not exist until the first massive stars exploded and scattered their fusion products through space. Subsequent generations of stars formed from gas enriched by these earlier explosions, incorporating heavier elements into their composition and the planets that formed around them. The Sun and Solar System represent products of this enrichment process, containing roughly 2% heavy elements by mass. Spectroscopic analysis reveals iron, carbon, oxygen, and dozens of other elements in the Sun's atmosphere, signatures of previous stellar generations that lived and died before our solar system formed. The oldest stars in the Milky Way's halo, formed within the first billion years of the galaxy's existence, contain hundreds of times less heavy element abundance than the Sun, while the youngest stars in active star-forming regions contain slightly more, reflecting ongoing enrichment as generations progress. This chemical evolution ties stellar life cycles to galactic timescales, connecting the physics of individual stars to the broader history of matter itself. The timescale for chemical enrichment depends on the star formation rate and the initial mass function, the distribution of stellar masses in newly formed populations. Massive stars, those exceeding 8 solar masses, burn their fuel rapidly and explode as supernovae within a few million to a few hundred million years. Less massive stars like the Sun evolve more slowly, living billions of years before shedding their processed material. The balance between these populations determines how quickly a galaxy enriches its interstellar gas with heavy elements. In the early universe, when star formation rates exceeded current values by factors of 10 or more, enrichment proceeded rapidly. Modern galaxies form stars at more sedate rates, adding heavy elements gradually as existing stellar populations age and contribute their processed material back to the interstellar medium. Galaxy mergers and interactions complicate this picture. When two galaxies collide, their gas clouds slam together, triggering waves of star formation that can exhaust a significant fraction of available fuel in a few hundred million years. These starburst galaxies form stars at rates hundreds of times higher than the Milky Way's current pace, producing brilliant young stellar populations and frequent supernovae. The combined feedback from stellar winds and explosions can drive remaining gas out of the galaxy entirely, terminating star formation and leaving behind an aging population of stars that gradually reddens as massive blue stars die, while longer-lived red stars persist. Many elliptical galaxies may have formed through this process, their smooth distributions and lack of star formation resulting from major mergers that consumed available gas billions of years ago. The interaction between the Milky Way and its satellite galaxies provides a local example of these processes at work. The Large and Small Magellanic Clouds orbit the Milky Way, trailing streams of gas stripped by tidal forces. Some of this material may eventually fall into the galactic disk, fueling future star formation. The Sagittarius Dwarf Elliptical Galaxy, discovered in 1994 despite lying on the far side of the galactic core, is being torn apart by the Milky Way's gravity. Its stars and dark matter are spreading into long tidal streams that wrap around the galaxy multiple times, gradually merging into the larger system. Over hundreds of millions of years, the dwarf galaxy will disappear entirely, its components absorbed into the Milky Way's halo. Similar accretion events likely occurred throughout galactic history, the Milky Way growing through consumption of smaller neighbours, while avoiding major mergers that would have destroyed its spiral structure. The dark matter halos surrounding galaxies extend far beyond the visible stellar populations, creating gravitational potentials deep enough to trap gas falling inward from intergalactic space. This accretion provides fuel for ongoing star formation, replenishing gas consumed in previous stellar generations. Without continuous infall, star formation would exhaust available gas within a few billion years, leaving galaxies passive and quiescent. The rate of infall appears to decline over cosmic time as dark energy dominates, and accelerating expansion reduces the flow of material between structures. In the distant future, galaxies may exhaust their fuel supplies completely, star formation ending not because supernovae expel all gas, but because no new material arrives to replace what stars consume. The distribution of dark matter itself reflects conditions in the very early universe. Dark matter particles, whatever their nature, decoupled from ordinary matter when the cosmos was less than a second old, too cool for the particles to interact frequently with the primordial plasma. From that moment forward, dark matter evolved under gravity alone, clumping into structures that served as gravitational seeds for galaxy formation. Computer simulations tracking billions of dark matter particles through cosmic history reproduce the filamentary cosmic web structure observed in galaxy surveys. The simulations begin with tiny density fluctuations derived from inflationary theory, then evolve those fluctuations forward through 13.8 billion years of gravitational collapse and structure formation. The results match observations remarkably well, successfully predicting the abundance and clustering properties of galaxies, the structure of dark matter halos, and the distribution of voids and filaments. These simulations also reveal substructure within dark matter halos, clumps and streams resulting from the hierarchical assembly process through which large halos formed by merging smaller ones. Some of this substructure may survive to the present day, creating localized overdensities as dark matter clumps orbit within the larger halo. If dark matter consists of massive particles, as many theories propose, these clumps might be detectable through their gravitational effects on stars or through direct detection experiments if Earth's orbit carries us through one. So far, no clear detection has occurred, though several claimed signals have generated controversy and require confirmation. The possibility that dark matter might not consist of particles at all, but might instead reflect a modification of gravity at large scales, has motivated alternative theories collectively called modified Newtonian dynamics, or MOND. These proposals adjust the gravitational force law to produce stronger effects at low accelerations, potentially explaining galactic rotation curves without requiring dark matter. Early MOND versions successfully reproduced many galaxy observations, but struggled to explain galaxy cluster dynamics and the cosmic microwave background fluctuation pattern without invoking additional unseen matter. More sophisticated versions, particularly those attempting to derive MOND-like behaviour from more fundamental theories, face challenges reproducing the full range of observations that dark matter models explain naturally. Most cosmologists regard particle dark matter as more likely, though minority viewpoints persist and contribute valuable scrutiny to mainstream models. The search for dark matter particles has expanded dramatically over the past few decades, employing multiple detection strategies. Direct detection experiments, typically located deep underground to shield against cosmic ray interference, watch for rare interactions between dark matter particles and atomic nuclei in ultra-pure detector materials. These experiments achieve extraordinary sensitivity, capable of detecting nuclear recoils depositing energies equivalent to a few dozen electron volts, but so far have found no convincing dark matter signal despite years of operation. The null results place increasingly stringent constraints on how strongly dark matter can interact with ordinary matter, ruling out large swathes of theoretical parameter space. Either dark matter interacts even more weakly than current experiments can detect, or it consists of something entirely different from the favoured weakly interacting massive particles that motivate most searches. Indirect detection strategies look for products of dark matter, particle annihilation, or decay. If dark matter particles occasionally collide and annihilate into gamma rays, neutrinos, or matter-antimatter pairs, these signals might appear as excess radiation from regions with high dark matter density, such as galactic centers or dwarf satellite galaxies. Several experiments have reported potential signals, including a gamma-ray excess from the Milky Way's core and an anomalous positron abundance in cosmic rays, but alternative explanations involving pulsars or other astrophysical sources remain viable. Distinguishing a dark matter signal from conventional astrophysical backgrounds requires understanding those backgrounds with precision that often proves difficult to achieve. Collider experiments at facilities like the Large Hadron Collider search for dark matter particles produced in high-energy collisions between protons. If dark matter consists of particles with masses accessible to current accelerators, collisions might create pairs of these particles along with visible particles like quarks or photons. The dark matter particles themselves would escape the detector without interacting, but their presence could be inferred from missing energy and momentum in the detected particles. No such signals have been conclusively identified, though searches continue as accelerators probe higher energies and analyze data with increasing sophistication. The lack of discoveries at the LHC has eliminated many popular dark matter models, particularly those predicting masses and interaction strengths within the ranges most thoroughly explored. Alternative dark matter candidates beyond particles also receive attention. Primordial black holes formed in the early universe before stars existed could constitute some or all of the dark matter. These objects would interact gravitationally like particle dark matter, but would be classical objects rather than quantum particles. Observations of gravitational microlensing, the temporary brightening of distant stars when a massive object passes in front of them, constrain how much dark matter can consist of compact objects in various mass ranges. The constraints rule out primordial black holes as the dominant dark matter component for most masses, though certain mass ranges remain viable. Recent detections of black hole mergers by gravitational wave observatories have renewed interest in whether some fraction of dark matter might hide in black holes of specific masses not yet fully constrained. Another exotic possibility involves axions, hypothetical particles originally proposed to solve a problem in quantum chromodynamics, but which could also serve as dark matter if they exist with appropriate properties. Axions would be extraordinarily light, potentially billions of times less massive than electrons, requiring different detection strategies than those used for heavier particle candidates. Specialized experiments search for axions by attempting to convert them into photons using strong magnetic fields, exploiting a predicted coupling between axions and electromagnetic fields. These searches explore frequency ranges corresponding to different axion masses, gradually covering the vast parameter space where axions might hide. No detection has occurred yet, but several experiments continue refining their sensitivity. The mystery of dark energy presents challenges even more profound than those surrounding dark matter. While dark matter at least behaves in ways consistent with particles or compact objects, differing from ordinary matter mainly in its failure to interact electromagnetically, dark energy exhibits properties that defy conventional understanding. Its density remains constant as the universe expands, meaning the total amount of dark energy increases over time, violating intuitions built from experience with matter and radiation. It exerts negative pressure, pushing space apart rather than resisting compression like normal substances, and its observed value sits roughly 120 orders of magnitude below the value quantum field theory naively predicts, suggesting either a spectacular cancellation of contributions or fundamental gaps in our theoretical framework. Some cosmologists propose that dark energy might not represent a new substance at all, but rather a breakdown of general relativity at cosmic scales. Perhaps Einstein's equations require modification when applied to the universe as a whole, with additional terms becoming important at extremely low curvatures or accelerations. Testing such proposals requires extremely precise measurements of cosmic expansion at different epochs, comparing how the expansion rate evolved over billions of years to the predictions of various modified gravity theories. Current observations slightly favour a cosmological constant over evolving dark energy, but uncertainties remain large enough that other possibilities cannot be ruled out definitively. The coincidence that dark energy's density currently roughly equals matter density after billions of years when one or the other dominated, strikes many physicists as requiring explanation. In the early universe, matter density far exceeded dark energy density due to matter's dilution as space expanded. but dark energy density remained constant, meaning its relative importance grew over time. Why do we live in the brief cosmic epoch when these two components have similar densities, rather than billions of years earlier when matter dominated completely, or billions of years in the future when dark energy will dominate entirely? This coincidence problem admits several potential resolutions, none entirely satisfactory. Perhaps our observations occur during this epoch precisely because earlier times would not have allowed complex structures like galaxies and stars to form, while later times might see structures ripped apart by accelerating expansion. This anthropic argument suggests that intelligent observers necessarily find themselves in a narrow window where conditions permit their existence. The anthropic principle in its various formulations attempts to explain apparently fine-tuned cosmic properties by noting that observers can only exist in universes where conditions permit their existence. If a multiverse contains regions with different physical laws or constants, life emerges only where parameters fall within narrow ranges that allow chemistry, stars, and stable atoms. Observers necessarily find themselves in such regions, however improbable those regions might be overall. This reasoning potentially explains not only dark energy's value, but also other seemingly arbitrary cosmic parameters like the strength of fundamental forces, the masses of elementary particles, and the amplitude of primordial density fluctuations. Critics argue that anthropic reasoning abandons the traditional scientific goal of deriving unique predictions from fundamental theory, replacing it with probabilistic arguments about observer selection effects. Supporters counter that if a multiverse actually exists, incorporating observer selection becomes necessary for connecting theory to observation. Whether or not anthropic reasoning proves correct, the fine-tuning of cosmic parameters for life appears genuine. The strong nuclear force, which binds protons and neutrons into atomic nuclei, needs to fall within a narrow range for carbon and oxygen to form in stars. Slightly weaker, and deuterium would not form, preventing hydrogen fusion in stars. Slightly stronger, and all hydrogen would have fused into heavier elements during the Big Bang, leaving none for water or organic chemistry. The electromagnetic force strength determines atomic sizes and chemical bond energies. Even modest changes would alter chemistry enough to prevent complex molecules like proteins or DNA from forming stable structures. The masses of quarks determine proton and neutron masses, which in turn affect the stability of atomic nuclei. Small shifts might make protons unstable, causing all matter to decay, or might make neutrons stable outside nuclei, preventing atoms from forming at all. The early universe's density fluctuations also appear finely tuned. Too large, and structures would have collapsed into black holes before stars could form. Too small, and gravity would never have pulled matter together into galaxies and stars, leaving the universe as a diffuse, expanding gas. The observed amplitude, roughly 1 part in 100,000, lies in a narrow range that permits hierarchical structure formation over billions of years. Inflation provides a mechanism for generating fluctuations with this amplitude, but the parameters governing inflation must themselves be chosen appropriately to produce the right fluctuation spectrum. Some versions of string theory suggest that these parameters are not truly fine-tuned, but arise naturally from the theory's internal structure, though proving this requires understanding string theory far better than current knowledge permits. String theory represents perhaps the most ambitious attempt to describe physics at the smallest possible scales, unifying quantum mechanics and general relativity within a single framework. The theory proposes that fundamental entities are not point particles but tiny vibrating strings, roughly a Planck length in size. Different vibrational modes of these strings correspond to different particles, much as different vibrational modes of a guitar string produce different musical notes. Gravitons, the hypothetical quantum particles mediating gravity, emerge naturally from string theory as one particular vibrational mode, providing a quantum description of gravity that has eluded other approaches. The theory requires additional spatial dimensions beyond the 3 we observe, typically 6 or 7 extra dimensions that must be compactified, curled up into shapes too small to detect directly. The geometry of these compactified dimensions determines the properties of particles and forces in the observable universe. Different compactification schemes yield different particle masses, force strengths, and coupling constants, creating a vast landscape of possible low-energy physics. Estimates suggest 10 to the 500 or more distinct compactifications might exist, each corresponding to a different set of physical laws. If string theory is correct and all these compactifications are realized somewhere in a multiverse, then the parameters we observe in our universe represent just one possibility among countless others, chosen not by fundamental theory, but by the requirement that observers can only exist where conditions permit complexity. This landscape scenario transforms questions about why cosmic parameters take particular values into questions about probability distributions across the multiverse. Rather than deriving unique values from first principles, physicists would need to calculate what fraction of universes have properties conducive to life and compare that to observations. The approach remains controversial, with critics arguing it lacks predictive power and supporters maintaining it represents the only viable path if the landscape actually exists. Resolution likely requires both better understanding of string theory's mathematical structure and improved observations that might reveal evidence for or against a multiverse, though the latter may prove fundamentally impossible if other universes lie beyond any possible observational horizon. Loop quantum gravity, an alternative approach to unifying quantum mechanics and general relativity, takes a different philosophical stance. Rather than treating gravity as an emergent phenomenon arising from string vibrations in a background spacetime, loop quantum gravity attempts to quantize spacetime itself. The theory describes space as woven from discrete loops, quantum states of gravitational fields that cannot be subdivided further. Area and volume become quantized, taking on discrete values separated by gaps, much as energy levels in atoms are quantized. At scales approaching the Planck length, smooth spacetime dissolves into this quantum foam, with geometry fluctuating wildly on timescales comparable to the Planck time, roughly 10 to the negative 43 seconds. Loop quantum gravity makes definite predictions about physics at extreme energies and curvatures, particularly regarding the Big Bang singularity. In classical general relativity, the early universe traces back to a point of infinite density and curvature where the equations break down. Loop quantum gravity suggests that quantum effects prevent this singularity, instead creating a bounce where a previous contracting phase transitions smoothly into the current expansion. This scenario, if correct, implies the Big Bang was not the beginning of time, but merely a transition point in an eternal cosmos. Observational tests of this prediction remain challenging, as signals from any pre-bounce era would be scrambled by the extreme conditions during the bounce itself. Some researchers propose that subtle patterns in the cosmic microwave background might preserve information about the bounce, though detecting such signals lies at or beyond current observational limits. Both string theory and loop quantum gravity attempt to describe physics at the Planck scale, where quantum gravity effects become important. At larger scales, both reduce to standard general relativity and quantum field theory, successfully describing observed phenomena. The Planck length, roughly 10 to the negative 35 meters, represents the distance at which quantum fluctuations in spacetime geometry become comparable to the background geometry itself. Attempting to probe distances shorter than this using particles requires energies high enough that the particles create black holes, preventing observation of subplanck physics through any direct means. This fundamental limitation suggests the Planck scale may represent an ultimate barrier to reductionism, a point beyond which the concept of smaller distances loses operational meaning. The full range of cosmic scale becomes most comprehensible when we arrange distances in powers of 10, each step representing a 10-fold increase in size. Begin at the Planck length, 10 to the negative 35 meters, the smallest distance where spacetime might possess definite structure. Move up by factors of 10. At 10 to the negative 34 meters, quantum foam dominates and classical geometry breaks down completely. At 10 to the negative 18 meters, we reach the scale where quarks and electrons might have internal structure, though none has been detected. At 10 to the negative 15 meters, atomic nuclei appear as composite objects made of protons and neutrons. At 10 to the negative 10 meters, atoms with their electron clouds define chemistry and material properties. At 10 to the negative 6 meters, bacteria become visible and biological systems operate. At 1 meter, human-scale objects and direct sensory perception define the realm of everyday experience. Continue upward. At 10 to the 3 meters, or 1 kilometer, geographical features like hills and small lakes become apparent. At 10 to the 6 meters, Continents and ocean basins span distances that humans can traverse but not directly perceive as unified structures. At 10 to the 7 meters, Earth's diameter provides our first planetary reference point. At 10 to the 9 meters, the distance from Earth to Moon represents the first step beyond our planet. At 10 to the 11 meters, or 100,000 kilometers, we reach roughly 1/3 the distance from Earth to Moon, while 10 to the 12 meters encompasses several times that separation. At 10 to the 14 meters, the Sun's distance from Earth defines the astronomical unit, the fundamental ruler for measuring the solar system. Moving outward, 10 to the 15th meters approaches 10 astronomical units, reaching beyond Mars toward Jupiter. At 10 to the 16th meters, roughly 100 astronomical units, we pass Neptune and approach the heliopause where the solar wind meets interstellar space. At 10 to the 17 meters, or 1,000 astronomical units, we enter the inner Oort cloud region, where long-period comets may originate. At 10 to the 18 meters, or roughly 1/10 of a light year, we reach perhaps the outer edge of the Sun's gravitational influence. At 10 to the 19 meters, or about 1 light year, we span a distance still smaller than the gap to Proxima Centauri, but beginning to approach interstellar scales. At 10 to the 20 meters, or about 10 light years, we encompass several dozen nearby star systems. At 10 to the 21 meters, 100 light years, we include most naked-eye visible stars and begin to sample the local galactic neighborhood. At 10 to the 22 meters, 1,000 light years, prominent nebulae like Orion become accessible and the diversity of stellar populations becomes apparent. At 10 to the 23 meters, 10,000 light years, we span a significant fraction of the galactic disk's thickness. At 10 to the 24 meters, 100,000 light years, the entire Milky Way fits within our measuring scale from edge to edge across the spiral disk. At 10 to the 25 meters, or about 300,000 light years, the local group begins to emerge, with Andromeda and the Milky Way plus their satellite galaxies defining a gravitationally bound system. At 10 to the 26 meters, several million light years, we encompass neighboring galaxy groups and begin to see the distribution of galaxies across space. At 10 to the 27 meters, tens of millions of light years, galaxy clusters like Virgo become apparent as distinct concentrations within a larger web of structure. At 10 to the 28th meters, hundreds of millions of light years, superclusters and voids define the cosmic web pattern, with matter distributed along filaments surrounding empty regions. At 10 to the 29 meters, billions of light years, we approach the scale of the observable universe's radius, encompassing the vast majority of visible galaxies and the full extent of structures accessible to observation. This progression spans roughly 64 orders of magnitude from Planck's scale to observable universe, a range so vast that human intuition completely fails to grasp it. Each order of magnitude represents a tenfold increase, meaning the observable universe exceeds the Planck length by a factor of 10 multiplied by itself 64 times. Written out, this number contains 64 zeros following the 1. No physical object in everyday experience varies across even 10 orders of magnitude. The largest things we regularly handle might be buildings a few hundred meters in size. The smallest might be dust particles around 10 micrometers, visible as motes in sunlight. This spans only 5 orders of magnitude, less than 1/10 the full cosmic range. Humans occupy a position remarkably close to the geometric mean of this scale, the point halfway between smallest and largest on a logarithmic scale. Our bodies measure roughly 1 meter, or 10 to the 0 meters, placing us about 32 orders of magnitude above the Planck scale, and 32 below the observable universe radius. This positioning may reflect fundamental constraints on the possible sizes of intelligent observers. Consciousness apparently requires complex information processing, which in turn requires large numbers of components interacting in organized ways. Brains contain roughly 100 billion neurons, each connecting to thousands of others through synapses, creating networks of staggering complexity. Building such systems requires objects large enough to accommodate vast numbers of molecular components, but small enough that signals can traverse the system in reasonable time. A nervous system the size of an atom could not contain enough components for complex thought. A brain the size of a planet would face insurmountable signal propagation delays, with nerve impulses requiring years to traverse its diameter even at light speed. The viable range for biological intelligence probably spans several orders of magnitude, from perhaps millimeters for the smallest possible nervous systems to tens of meters for the largest, with most implementations falling in the centimeter to meter range. Similar arguments constrain the possible sizes of technological devices. Computers require components small enough for rapid switching, but large enough for reliable fabrication and operation. Current microprocessors use transistors measuring tens of nanometers, approaching limits imposed by quantum tunneling and heat dissipation. Future technologies might push toward molecular or atomic scale components, but fundamental constraints eventually intervene. The distribution of structure across cosmic scales follows patterns determined by fundamental physics. At the smallest scales, quantum mechanics dominates, with uncertainty principles preventing precise simultaneous knowledge of position and momentum. Particles exist as probability clouds rather than point objects, their properties defined only statistically until measurement forces a definite outcome. At intermediate scales from atoms to stars, classical physics provides adequate description. Objects follow deterministic trajectories, their properties well defined and measurable with arbitrary precision given sufficient care. Electromagnetic and gravitational forces govern interactions, with quantum effects appearing mainly in atomic and molecular processes that underlie chemistry and material properties. At the largest scales, general relativity becomes necessary to describe space-time curvature and cosmic expansion. The universe's geometry deviates from simple Euclidean space, with matter and energy curving space-time and that curvature influencing how matter moves. The distinction between space and time blurs, becoming coordinate-dependent choices rather than absolute structures. Observers moving at different velocities experience time differently, their clocks running at different rates, and their measurements of simultaneity disagreeing. These relativistic effects remain small at human scales, but become crucial for understanding black holes, gravitational waves, and cosmic expansion. The hierarchy of forces operating at different scales creates distinct regimes where different physical processes dominate. The strong nuclear force responsible for binding quarks into protons and neutrons and holding atomic nuclei together operates only at distances below a few femtometers, roughly 10 to the negative 15 meters. Beyond this range, its strength drops essentially to zero, making it irrelevant for chemistry, biology, or any process involving separated atoms. The weak nuclear force governing certain radioactive decay processes and neutrino interactions operates at even shorter ranges, below 10 to the negative 18 meters. Its effects appear mainly in particle physics experiments and astrophysical environments with extreme temperatures or densities. The electromagnetic force, mediated by photons, follows an inverse square law that allows it to operate across arbitrary distances, though its strength diminishes with separation. This force dominates chemistry and biology, holding atoms together, creating molecular bonds, and generating the electrical signals that propagate through nervous systems. Light itself represents electromagnetic radiation, photons carrying energy and momentum across cosmic distances. The electromagnetic spectrum spans from radio waves with wavelengths measuring kilometers to gamma rays with wavelengths smaller than atomic nuclei, a range exceeding 20 orders of magnitude in frequency. Different wavelength ranges probe different physical processes and reveal different aspects of cosmic structure. Gravity, the weakest force at small scales, becomes dominant at large distances because it acts only attractively and because electromagnetic forces typically balance between positive and negative charges, cancelling at macroscopic scales. A single electron and proton separated by 1 meter experience electromagnetic attraction roughly 10 to the 39th times stronger than their gravitational attraction. Yet gravity shapes the cosmos because large objects contain nearly equal numbers of protons and electrons, their electromagnetic effects cancelling while gravity accumulates. Planets, stars, galaxies, and the universe's large-scale structure all arise from gravitational collapse and dynamics, with other forces playing secondary roles. The weakness of gravity at small scales presents both a mystery and an opportunity. Why does gravity couple so much more weakly to matter than other forces? Proposed explanations range from extra dimensions that dilute gravity's strength to anthropic arguments that strong gravity would prevent star formation, and hence observers. The weakness also means that quantum gravity effects remain negligible, except at extreme conditions near black hole singularities or during the universe's first instance. Ordinary laboratory experiments, even at the highest energies accessible to particle accelerators, probe nowhere near the Planck scale where quantum gravity becomes important. This experimental inaccessibility makes testing theories of quantum gravity extraordinarily difficult, forcing theorists to rely on mathematical consistency and indirect cosmological observations rather than controlled experiments. Black holes represent perhaps the most extreme environments where scale considerations become crucial. These objects pack enormous mass into volumes defined by their event horizons, surfaces from which not even light escapes. The horizon radius scales linearly with mass. A black hole containing one solar mass has a horizon roughly 3 kilometers in radius, while a supermassive black hole with 1 billion solar masses has a horizon 3 billion kilometers across, roughly the distance from the Sun to Neptune. Despite this size difference, the physical conditions at the horizon remain similar in some respects. An observer falling through would notice nothing special at the moment of crossing, experiencing only free fall with no local indication that escape has become impossible. But the tidal forces stretching objects falling into black holes depend critically on the hole's mass. Near a stellar mass black hole's horizon, tidal forces become extreme. An astronaut falling feet first would be stretched vertically and compressed horizontally by gravitational gradients that increase as the inverse cube of distance from the hole's center. These forces would tear a human body apart well before reaching the horizon, a process sometimes called spaghettification. Near a supermassive black hole's horizon, however, the gentler gravitational gradient allows objects to cross intact. The tidal forces, while present, remain below the threshold needed to disrupt ordinary matter. An astronaut could theoretically fall through the horizon of a billion solar mass black hole without immediate harm, though this would inevitably reach the central singularity within a predictable time after crossing, their fate sealed despite no local indication of doom at the horizon itself. Inside the horizon, space-time curvature becomes so extreme that all future paths lead toward the singularity, a point or region where curvature diverges to infinity and general relativity breaks down. What happens at this singularity remains unknown because the theory predicting its existence also admits its own failure there. Quantum gravity effects, whatever form they take, presumably become important at or near the singularity, potentially resolving the infinite curvature into some gentler quantum structure. But without a complete theory of quantum gravity, the singularity's true nature remains speculation. Some proposals suggest singularities might connect to other regions of space-time, creating wormholes or bridges to distant locations or even other universes. Others propose that quantum effects create a bounce, converting the collapsing matter into an expanding region that might bud off as a new universe disconnected from our own. Black holes also evaporate through Hawking radiation, a quantum process that slowly converts their mass into thermal radiation. The temperature of this radiation scales inversely with mass. Stellar mass black holes radiate at billionths of a degree above absolute zero, while microscopic black holes, if they existed, would radiate at tremendous temperatures and evaporate almost instantly. A black hole with 1 billion solar masses has a temperature of roughly 10 to the negative 16 Kelvin, far colder than the cosmic microwave background. Such holes actually grow by absorbing background radiation faster than they evaporate. Only in the far future, when the universe has expanded and cooled enough that the microwave background temperature drops below individual black holes' Hawking temperatures, will evaporation dominate over accretion. The evaporation timescale also scales with mass, specifically as mass cubed. A solar mass black hole requires roughly 10 to the 67 years to evaporate completely, far longer than the current age of the universe. A supermassive black hole with 1 billion solar masses persists for 10 to the 100 years, an almost incomprehensible duration. During this time, the hole slowly loses mass, its horizon shrinking and its temperature rising. As the hole becomes smaller, evaporation accelerates, eventually reaching a runaway phase where the remaining mass disappears in a burst of radiation. Whether this final explosion releases all information about what fell into the hole, or whether information is lost forever, remains one of the most debated questions in theoretical physics, touching on deep issues about the compatibility of quantum mechanics and general relativity. The information paradox arises because quantum mechanics insists that information cannot be destroyed, while classical general relativity suggests that anything falling into a black hole leaves no imprint on the external universe except through its contribution to the hole's mass, charge, and spin. If a black hole evaporates completely, converting its mass to thermal radiation that carries no information about the hole's formation, then information appears to be lost, violating quantum mechanics. Proposed resolutions include suggestions that information somehow encodes itself in subtle correlations within the Hawking radiation, or that remnants persist after evaporation, tiny stable objects containing all the information that fell in, or that black holes do not evaporate completely but leave behind Planck-scale relics. Recent work on holography and the ADS-CFT correspondence suggests information might be preserved, though the precise mechanism remains unclear and controversial. The holographic principle, emerging from black hole thermodynamics and string theory, proposes that all information contained within a volume of space can be encoded on the boundary of that volume, much as a hologram encodes three-dimensional images on two-dimensional surfaces. Applied to black holes, this suggests that information about matter falling through the event horizon never truly enters the interior, but instead remains encoded on the horizon itself. The horizon's area, measured in Planck units, equals the maximum entropy the black hole can contain, with each Planck area unit corresponding to one bit of information. This relationship holds universally for black holes regardless of mass, connecting thermodynamics, quantum mechanics, and gravity in ways that remain incompletely understood but seem fundamental to spacetime's nature. Extending holography beyond black holes leads to profound implications for cosmic scale. If the observable universe itself acts like a bounded region, perhaps its information content is finite, determined by the area of its cosmological horizon rather than its volume. This would place an upper limit on the number of distinguishable quantum states accessible to observation, making the observable cosmos finite in information content despite containing astronomical numbers of particles and vast volumes of space. Some calculations suggest the observable universe might contain approximately 10 to the 120 bits of information, a number vastly larger than the number of atoms but still finite. Whether this limit has physical meaning or represents merely a mathematical curiosity depends on questions about quantum gravity that remain unresolved. The concept of scale invariance, where physical laws or structures look similar across different magnifications, appears in limited context throughout physics. Fractals, mathematical objects exhibiting self-similarity at all scales, rarely occur in nature except as approximations. Coastlines show statistical self-similarity over limited scale ranges, their jagged appearance persisting from kilometers down to meters before molecular structure takes over. Some biological structures, particularly in plants and circulatory systems, exhibit approximate fractal properties that optimize resource distribution. But the universe as a whole breaks scale invariance dramatically. Atoms behave nothing like stars, and stars behave nothing like galaxies. Each scale regime possesses distinctive physics with no simple rescaling relationship to larger or smaller regimes. Dimensional analysis provides a powerful tool for understanding how physical quantities must scale. Kepler's third law, relating orbital periods to orbital radii, follows from dimensional considerations alone once you know gravity creates the relevant force. The law states that the square of a planet's orbital period equals a constant times the cube of its orbital radius, with a constant determined by the central mass. This scaling relationship means that doubling the orbital radius increases the period by a factor of roughly 2.8, the square root of 8. The relationship holds whether applied to planets orbiting the Sun, moons orbiting planets, or stars orbiting galactic centers, demonstrating how fundamental physics constrains possible behaviors across vast-scale differences. Similarly, the Stefan-Boltzmann law governs thermal radiation from hot objects, stating that radiated power scales as the fourth power of temperature. A star twice as hot radiates 16 times more power per unit surface area. Combined with the relationship between stellar luminosity, radius, and temperature, this scaling explains why massive stars, which burn hotter due to higher core pressures, shine thousands to millions of times more brightly than the Sun despite being only several times larger. The scaling relationships built into physical laws constrain how objects of different sizes can behave, creating predictable patterns across cosmic scales despite the enormous range of conditions involved. The number of particles in various systems provides another perspective on scale. A human body contains roughly 10 to the 28th atoms, mostly hydrogen, oxygen, and carbon. Earth contains about 10 to the 50 atoms. The Sun contains 10 to the 57 atoms. The Milky Way, with its few hundred billion stars plus interstellar gas, contains perhaps 10 to the 68 atoms of ordinary matter. The observable universe contains roughly 10 to the 80 atoms, a number so large that expressing it requires 80 zeros after the 1. Yet even this vast quantity remains infinitesimal compared to the number of possible quantum states those atoms could occupy. A single hydrogen atom has infinitely many possible energy states, though only the lowest few are commonly occupied at typical temperatures. A system of 10 to the 80 atoms has vastly more possible configurations than there are atoms in the universe raised to itself many times over. This combinatorial explosion of possibilities underlies statistical mechanics and thermodynamics. The second law of thermodynamics, stating that entropy increases in closed systems, reflects the overwhelming probability that systems evolve toward high entropy states simply because far more configurations correspond to high entropy than low entropy. A gas confined to one corner of a box can spread throughout the container by exploring all possible configurations, and the number of spread out configurations vastly exceeds the number where molecules cluster together. Gravity complicates this picture because gravitating systems can decrease their entropy locally while increasing it globally. Forming concentrated structures like stars and galaxies that represent local entropy, decreases offset by larger entropy, increases in radiated heat. The arrow of time, the observed asymmetry between past and future, appears to stem from the universe's initial low entropy state. The Big Bang began with matter distributed remarkably uniformly, a configuration of extraordinarily low gravitational entropy. Subsequent gravitational collapse formed stars, galaxies, and clusters, structures that seem more organized than the initial smooth distribution, but actually represent entropy increase when properly accounting for gravitational degrees of freedom. The eventual heat death, with matter dispersed in maximum entropy equilibrium, represents the final state toward which the second law drives cosmic evolution. Time's arrow emerges from this progression from low to high entropy, explaining why we remember the past but not the future, and why broken eggs do not spontaneously reassemble. Measuring cosmic scales requires carefully calibrated distance indicators, each applicable over different ranges. Parallax, the apparent shift in nearby stars' positions as Earth orbits the Sun, works reliably out to several hundred light-years, but becomes too small to measure accurately for more distant objects. Standard candles like Cepheid variable stars, whose intrinsic brightness correlates with their pulsation period, extend the distance ladder to tens of millions of light-years. Type Ia supernovae reach billions of light-years, their standardized peak brightness allowing distance determination for galaxies too remote for Cepheids to be resolved individually. Each rung on this distance ladder calibrates against the previous one, building a chain from parallax measurements of nearby stars ultimately to the most distant galaxies observed. Uncertainties accumulate with each rung, making precise distance measurements at cosmic scales challenging. The Hubble constant, quantifying how fast the universe expands, remains uncertain at the few percent level despite decades of intensive study. Different measurement techniques yield values differing by more than their stated uncertainties, a tension that might indicate systematic errors in distance measurements, unknown physics affecting observations, or genuine problems with the standard cosmological model. Resolving this Hubble tension has become a priority for observational cosmology, requiring improved distance calibrations and better understanding of potential systematic effects. The cosmic distance ladder also relies on assumptions about how light propagates through space and how cosmic expansion affects observations. Light travelling from distant galaxies passes through intergalactic gas, dark matter concentrations, and varying space-time curvature, each potentially affecting the photon's path and energy. Gravitational lensing by intervening mass concentrations bends light rays, sometimes creating multiple images of the same background galaxy, or magnifying and distorting its appearance. Strong lensing produces dramatic effects like Einstein rings, where a background galaxy's light bends around a foreground cluster into nearly complete circles. Weak lensing creates subtle distortions, stretching galaxy images by a few percent in statistically predictable patterns. These effects must be accounted for when using distant objects as standard candles or rulers for measuring cosmic expansion. Redshift measurements provide the most direct observational access to cosmic distances at large scales. When a galaxy's spectrum shows spectral lines shifted to longer wavelengths compared to laboratory measurements, that shift encodes information about the galaxy's distance through the expansion of space. For nearby galaxies, redshift translates simply into recession velocity through the Doppler formula. But at large distances where recession speeds approach light speed, relativistic corrections become necessary, and the relationship between redshift and distance depends on the universe's expansion history. A galaxy observed with redshift of 1 appears roughly half the size it would if the universe were not expanding, because space has doubled since the light was emitted. At redshift 2, space has tripled. At redshift 7, space has expanded 8-fold, meaning galaxies observed at this redshift appear as they existed when the universe was 1/8 its current size. The highest redshifts detected exceed 13, corresponding to galaxies observed less than 300 million years after the Big Bang. These early galaxies appear small, irregular, and actively forming stars at prodigious rates. Their light has travelled for more than 13 billion years to reach us, stretched by cosmic expansion from ultraviolet wavelengths into the infrared. Observing these distant systems requires space telescopes sensitive to infrared light, since Earth's atmosphere absorbs most infrared wavelengths. The James Webb Space Telescope, launched in 2021, specialises in detecting this ancient light, peering deeper into cosmic history than any previous observatory. Early results reveal galaxies at higher redshifts and earlier epochs than expected, some appearing surprisingly mature despite forming so soon after the Big Bang. These observations challenge models of early galaxy formation, suggesting that supermassive black holes and large stellar populations assembled more rapidly than simulations predict. Either stars formed more efficiently in the early universe than current models assume, or some formation process we do not yet understand accelerated the assembly of the first galaxies. The discrepancy illustrates how pushing observations to new scales often reveals phenomena requiring explanation, driving refinement of theoretical models. Each new generation of telescopes has discovered unexpected features in the cosmos, from quasars in the 1960s to dark energy in the 1990s, to these early massive galaxies in the 2020s. The cosmic microwave background places the most stringent constraints on cosmological models, because it provides a snapshot of conditions throughout the observable universe at a specific early epoch. The tiny temperature fluctuations imprinted on this background encode information about the universe's composition, geometry, and expansion history with remarkable precision. Measurements by satellites like WMAP and Planck have determined key cosmological parameters to better than 1% accuracy, establishing the standard cosmological model on firm observational footing. The universe is spatially flat to within measurement precision. Its composition includes roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. Its age equals 13.8 billion years with uncertainty of only tens of millions of years. Yet this precise standard model rests on assumptions that might not hold. The cosmological principle assumes the universe is homogeneous and isotropic at large scales, looking roughly the same in all directions from any location. This assumption simplifies the mathematics of cosmology dramatically, but remains an assumption rather than a proven fact. We can only observe the universe from one location, our own, making it impossible to verify that other locations see similar large-scale structure. The cosmic microwave background appears remarkably uniform across the sky, supporting isotropy from our position, but offers no direct evidence about homogeneity at locations billions of light-years from Earth. Some cosmologists propose inhomogeneous models where the Milky Way occupies a special position in an underdense void, potentially explaining observational puzzles like the Hubble tension without invoking dark energy. Most such models struggle to explain other observations, particularly the microwave background fluctuation pattern, but they illustrate that alternatives to the standard model remain conceivable. The observable universe's finite size and age place fundamental limits on what we can learn about cosmic structure at the very largest scales. We observe only a sphere roughly 93 billion light-years in diameter, the distance light could travel while accounting for expansion during the universe's 13.8 billion year history. Beyond this horizon, light has not had time to reach us, rendering those regions forever unobservable unless expansion dramatically slows or reverses. If the universe extends far beyond the observable region, as most cosmologists expect, then cosmic structures larger than our observable volume could exist but remain undetectable. The cosmic web we observe might be merely one small patch in a far vaster pattern, or the universe might be fundamentally inhomogeneous, at scales exceeding what we can measure. Some observational hints suggest structure at scales approaching or exceeding the horizon size. Surveys mapping galaxy positions have identified apparent voids and superclusters with sizes reaching hundreds of millions of light years, approaching the scale where the cosmological principle should ensure uniformity. A few researchers claim to detect correlations in galaxy clustering at scales exceeding 1 billion light-years, potentially violating the principle. But these claims remain controversial, with statistical uncertainties large enough that chance alignments might explain the observations. As surveys catalogue more galaxies across larger volumes, clearer pictures of the larger scale structure should emerge, either confirming the cosmological principle or revealing deviations that require new physics or modifications to standard models. The multiverse concept extends cosmic scale to its logical extreme, proposing that our observable universe represents one region within a vastly larger ensemble of causally disconnected domains. These domains might result from eternal inflation, quantum branching, string theory's landscape of vacuum states, or other mechanisms that produce multiple distinct regions with potentially different physical laws. If such a multiverse exists, asking about the universe's total size becomes meaningless because no single number describes it. Different domains might have different dimensionalities, different force strengths, different particle content. Our domain happens to have properties allowing observers to emerge, but countless other domains might be sterile, devoid of any complexity or life. Testing multiverse proposals faces severe obstacles because other domains, by definition, lie beyond observational access. If no signal can propagate from other universes to ours, then no experiment can detect them, rendering the multiverse hypothesis unfalsifiable in the traditional scientific sense. Some theorists argue this makes multiverse ideas metaphysical rather than scientific, removing them from the realm of proper physics. Others counter that if a well-established theory like inflation or string theory predicts a multiverse as an unavoidable consequence, then we must take that prediction seriously, even if we cannot test it directly. The debate reflects deeper questions about what constitutes legitimate scientific theorizing when direct observation becomes impossible in principle. Indirect tests might still constrain multiverse models. If our universe's properties represent typical values drawn from a probability distribution over possible universes, then measuring those properties and comparing them to predictions could support or challenge multiverse scenarios. The cosmological constant provides one example. Observations show it has a small positive value, roughly consistent with anthropic predictions that it cannot be much larger without preventing galaxy formation. If we'd found it to be 0 or negative, that would have challenged anthropic multiverse explanations. Similarly, if we discover that fundamental constants vary across our observable region, that might indicate we inhabit a boundary between different vacuum states, supporting multiverse ideas. So far, no such variations have been detected, with measurements showing constants remain uniform across billions of light years. The question of whether the universe is finite or infinite in spatial extent remains unresolved. Observations indicate spatial flatness, consistent with either an infinite flat space or a very large but finite topology that curves back on itself at scales far exceeding the observable horizon. A finite topology might create detectable patterns if the universe is small enough that light could have travelled completely around it since the Big Bang, creating multiple images of the same cosmic structures in different directions. Searches for such patterns in the microwave background have found nothing, constraining any closure scale to be larger than the observable universe radius. An infinite universe extends forever with no boundary, containing infinite matter and infinite copies of any finite configuration. A finite but unbounded universe wraps around on itself like the surface of a sphere, containing finite matter but no edge. Both possibilities challenge intuition in different ways, An infinite universe seems difficult to comprehend because infinity suggests inexhaustible extent, yet we can only ever observe a finite portion. A finite universe prompts questions about what lies outside, though the question itself may be meaningless if space ends not at a boundary, but through topological closure. General relativity permits both geometries and offers no compelling reason to prefer one over the other based solely on theoretical considerations. Only observations can determine which describes our universe, and current data remain consistent with both infinite flat space and very large finite spaces with undetectable curvature. Scale considerations pervade attempts to formulate physical theories at the most fundamental level. Effective field theories, which describe physics at accessible energies, incorporate only the degrees of freedom relevant at particular scales. Quantum electrodynamics describes electrons and photons without explicit reference to quarks or weak interactions, because those aspects of physics become important only at higher energies or shorter distances. At low energies, they contribute negligible effects that can be absorbed into measured parameters, like electron mass and charge. This scale separation allows physicists to make predictions without solving all of physics simultaneously, focusing on relevant scales for the problem at hand. But this approach breaks down when probing energies approaching the Planck scale, where quantum gravity effects become important, and all known forces potentially unify. At these energies, conventional effective field theory fails because the separation between scales disappears. Gravity can no longer be treated as a minor perturbation on flat spacetime, and quantum corrections diverge unless the theory possesses special cancellations or symmetries. String theory attempts to resolve these infinities by replacing point particles with extended strings whose finite size regulates ultraviolet divergences. Loop quantum gravity takes a different approach, discretizing space-time itself to eliminate infinities. Both remain incomplete theories with many open questions about their mathematical consistency and connection to observed physics. The hierarchy problem in particle physics asks why the Higgs boson mass, measured at 125 giga-electron-volts, sits so far below the Planck energy of 10 to the 19 giga-electron-volts. Quantum corrections should push scalar particle masses toward the Planck scale unless extraordinary fine-tuning or new physics intervenes. Supersymmetry, which proposes a symmetry between matter particles and force carriers, provides one potential solution by arranging cancellations between competing quantum corrections. But experiments at the Large Hadron Collider have found no evidence for supersymmetric particles at energies up to several tera-electron-volts, constraining or ruling out many simple supersymmetric models. Alternative solutions include extra dimensions where the fundamental Planck scale is actually much lower than it appears, or anthropic selection if a multiverse contains regions with varying Higgs masses. These questions about fundamental physics connect intimately to cosmic scale, because the early universe provided conditions approaching Planck energies where quantum gravity matters. The first instance after the Big Bang, when the universe was smaller than a proton and hotter than 10 to the 32nd Kelvin, represent a natural laboratory for testing theories of physics at the highest energies. Unfortunately, this laboratory existed 13.8 billion years ago and cannot be recreated experimentally. Colliders can reach energies of tens of tera-electron-volts, impressive by human standards, but still 16 orders of magnitude below Planck energies. No conceivable technology could build an accelerator reaching Planck scales, because the required energy density would create a black hole before achieving the desired collision energy. Cosmological observations provide the only accessible data about Planck scale physics, encoded in patterns left by processes occurring during inflation or earlier. The cosmic microwave background fluctuations preserve information about quantum processes that occurred when the universe was 10 to the negative 35 seconds old, and structures now spanning hundreds of millions of light-years were smaller than atoms. Gravitational waves from inflation, if detected, would probe energies within a few orders of magnitude of the Planck scale, providing unprecedented insight into quantum gravity. Several experiments search for these primordial gravitational waves by measuring subtle polarization patterns they would imprint on the microwave background. No detection has occurred yet, with increasingly sensitive upper limits constraining the energy scale of inflation to lie below 10 to the 16th giga-electron-volts, still well above energies accessible to colliders but below some theoretical predictions. The relationship between microscopic quantum processes and macroscopic cosmic structure illustrates how scale bridges connect different domains of physics. Quantum fluctuations during inflation, variations in energy density at subatomic scales governed by Heisenberg's uncertainty principle, became frozen into classical density perturbations as they stretched beyond the horizon. These perturbations, initially spanning less than a Planck length, grew to cosmic proportions while maintaining their amplitude and statistical properties. When the universe later expanded enough that these scales re-entered the horizon, they seeded structure formation through gravitational collapse. The galaxies and clusters we observe today trace their origins to quantum fluctuations that occurred at the smallest possible scales, demonstrating a direct causal chain from Planck-scale physics to structures spanning millions of light-years. This amplification from quantum to classical, from microscopic to macroscopic, represents one of the most remarkable aspects of cosmic evolution. In laboratory settings, quantum effects typically remain confined to atomic or smaller scales. Macroscopic objects behave classically because quantum coherence degrades through interactions with the environment, a process called decoherence. But during inflation, quantum fluctuations avoided decoherence by stretching faster than light could propagate, isolating different regions from causal contact. Each fluctuation evolved independently, its quantum nature preserved even as its physical size exceeded astronomical dimensions. Only much later, when expansion slowed and these scales re-entered causal contact, did classical behavior emerge. The cosmic microwave background fluctuations represent quantum mechanics writ large across the sky, probability distributions made manifest in temperature variations visible to microwave telescopes. The connection between smallest and larger scales appears in other contexts as well. Vacuum energy, if it exists as quantum field theory suggests, contributes to spacetime curvature and cosmic expansion, despite arising from subatomic quantum processes. The cosmological constant measures roughly 10 to the negative 47 inverse square meters in natural units, an incredibly small curvature scale corresponding to the size of the observable universe. Yet this value determines the universe's ultimate fate, controlling whether expansion accelerates or decelerates over cosmic history. How Planck scale vacuum fluctuations produce exactly this value, differing from naive predictions by 120 orders of magnitude, remains completely unexplained. The discrepancy suggests either profound gaps in our understanding of quantum field theory, gravity, or both, or alternatively that some unknown mechanism cancels the vast majority of vacuum energy contributions. Anthropic reasoning applies here because if vacuum energy were much larger in magnitude, the universe would have either collapsed quickly or expanded so rapidly that structures could never form. Life requires stars, which require galaxies, which require the slow, steady expansion that allows gravitational collapse to overcome cosmic expansion in localized regions. A universe with vacuum energy exceeding the observed value by even a few orders of magnitude might expand too rapidly for structures to assemble, rendering it sterile and lifeless. If countless universes exist with varying vacuum energies, observers necessarily emerge only in those rare examples where the value permits structure formation. This selection effect might explain why we observe such an improbably small vacuum energy, not because fundamental physics prefers this value, but because observers cannot exist elsewhere. Critics of anthropic reasoning note that it sacrifices predictive power. Rather than deriving unique values for physical constants, anthropic arguments merely constrain them to ranges compatible with life, leaving vast parameter spaces unexplored. Multiple different combinations of constants might permit observers, making it impossible to predict which combination actually occurs without additional principles. Some versions of anthropic reasoning also face the measure problem: how to count or weight different universes in a multiverse when calculating probabilities. If infinitely many universes exist with different properties, what measure determines the probability of observing particular values? Different measures give different answers, and no obvious principle selects the correct measure. These technical difficulties, combined with philosophical qualms about explaining observations through selection effects, keep anthropic reasoning controversial despite its potential to address otherwise intractable fine-tuning problems. The scale dependence of physical laws manifests clearly in the running of coupling constants, fundamental parameters whose effective values change with energy or distance scale. The electromagnetic fine structure constant, measuring the strength of electromagnetic interactions equals approximately 1 over 137 at low energies, but increases to roughly 1 over 128 at energies of 100 giga-electron-volts. This running occurs because virtual particle pairs in the quantum vacuum screen electric charges, reducing their apparent strength at large distances. At short distances corresponding to high energies, this screening becomes less effective, making the coupling appear stronger. The strong nuclear force coupling runs in the opposite direction, growing weaker at high energies through a property called asymptotic freedom. Quarks interact strongly at low energies, binding them permanently into protons and neutrons. But at very high energies they behave almost like free particles, their interactions becoming perturbatively calculable. This energy-dependent behavior means that the strengths of different forces converge or diverge depending on the scale considered. At energies around 10 to the 16th giga-electron-volts, the electromagnetic, weak and strong couplings nearly meet, suggesting they might unify into a single force at higher energies. Grand unified theories propose exactly such unification, predicting that what appear as distinct forces at low energies are actually different aspects of one fundamental interaction. Experiments searching for proton decay, predicted by many grand unified theories, have found no evidence after decades of observation, constraining or ruling out the simplest unification schemes. But more complex models remain viable, and the apparent convergence of couplings continues to suggest that unification occurs somewhere near the grand unified scale. The Planck scale represents the ultimate convergence point where gravity joins the other forces in a complete unified theory. At this energy, roughly 10 to the 19th giga-electron-volts, quantum corrections to gravity become as important as classical gravitational effects, and space-time itself exhibits quantum behavior. Below this scale, gravity can be treated classically while other forces are quantized. Above this scale, if the concept of above even makes sense, all forces require quantum description and presumably unify in some manner. String theory proposes that this unification occurs because all particles and forces arise from different vibration modes of fundamental strings. The theory naturally includes gravitons and predicts gravitational interactions consistent with general relativity at low energies while remaining finite and well-behaved at Planck scale energies. Whether string theory or some alternative correctly describes Planck scale physics remains an open question, perhaps unanswerable given experimental inaccessibility. But the fact that a quantum theory of gravity must exist and that it must reduce to known physics at accessible scales constrains possibilities significantly. Any successful theory must explain black hole thermodynamics, reproduce general relativity in the appropriate limit, and unify consistently with quantum field theory. These requirements eliminate vast classes of potential theories, leaving relatively few candidates that satisfy all constraints. The challenge lies in distinguishing, among remaining possibilities, when direct experimental tests remain beyond reach, and mathematical analysis of these theories stretches current techniques to their limits. The measurement limitations imposed by quantum mechanics add another layer to considerations of cosmic scale. Heisenberg's uncertainty principle states that position and momentum cannot both be measured with arbitrary precision simultaneously. The product of their uncertainties must exceed a minimum value set by Planck's constant. For everyday objects, this limit remains negligibly small, but for microscopic particles it becomes significant. An electron's position can be measured to within an angstrom, but doing so renders its momentum uncertain by at least 10 to the negative 24 kg-meters per second, enough to completely randomize its trajectory. This fundamental limitation means that asking where an electron is and how fast it moves has no precise answer, even in principle, not because of experimental inadequacy, but because the electron itself does not possess simultaneous definite values for these properties. This quantum uncertainty extends to energy and time through a parallel relation. Measuring energy precisely requires long observation times, while brief measurements leave energy uncertain. For the universe itself, this creates interesting constraints. The total energy of the cosmos, including matter, radiation, dark energy, and gravitational potential, might equal exactly zero when properly accounting for gravity's negative energy contribution. Some calculations in general relativity suggest closed universes have exactly zero total energy, while flat or open universes might have positive energy. If the total energy is zero, then quantum uncertainty places no constraint on the universe's duration. It could persist forever without violating energy conservation, because no net energy needs to be borrowed from the quantum vacuum. This result suggests the universe might be a quantum fluctuation that avoided vanishing because its total energy equals zero, though this interpretation remains speculative and controversial. Observer effects complicate measurements at all scales. In quantum mechanics, observation disturbs what is observed, collapsing probability distributions into definite values through the measurement process. For cosmic observations, the disturbance comes not from measurement apparatus, but from the finite speed of light and expansion of space. We observe distant galaxies as they were billions of years ago, their current states unknown and in principle unknowable, because information about their present condition has not yet reached us. Asking what a galaxy 10 billion light-years away looks like right now has no answer within our light cone. That galaxy exists in our past, its current state lying in a region of space-time causally disconnected from us. Only its past, recorded in photons now arriving at Earth, can be observed. This observational constraint means that mapping the universe's current state is impossible. We can map its past light cone, the set of events from which light could have reached us by now, but cannot construct a complete spatial slice representing all of space at the present moment. Different observers, moving at different velocities, would not even agree on which events are simultaneous, relativity rendering the notion of universal now meaningless. The universe possesses no objective present, only the local present experienced by individual observers and the larger structure of space-time within which different observers carve out different notions of simultaneity. This relativity of simultaneity becomes increasingly important at cosmic scales, though its effects remain small for observers moving slowly compared to light. The cosmological horizon creates an informational boundary analogous to black hole event horizons. Just as nothing inside a black hole's event horizon can send signals outward, nothing beyond the cosmological horizon can send signals to us. The horizon's radius, roughly 46 billion light-years, defines the maximum distance from which light could have travelled since the Big Bang, accounting for expansion. This horizon is not a physical surface, but rather a sphere centred on our location, marking the limit of potential observation. Other observers elsewhere in the universe have their own horizons centred on their positions, overlapping partially with ours but extending into regions we cannot see. If the universe is infinite, most of it lies beyond everyone's horizon, forever inaccessible to observation regardless of how long we wait or how powerful our telescopes become. Accelerating expansion driven by dark energy means the cosmological horizon will not expand indefinitely. In a decelerating universe, the horizon grows steadily as light from progressively more distant regions has time to reach us. But in an accelerating universe, distant regions recede so rapidly that their light, though emitted in our direction, loses the race against expansion and never arrives. The acceleration creates an effective event horizon beyond which events remain forever unobservable. This De Sitter horizon, named after Willem de Sitter who first studied such spacetimes, sits at a distance where recession velocity equals light speed. For our universe's observed dark energy density, this horizon lies roughly 16 billion light-years away, closer than the cosmological horizon from which we currently receive light emitted in the early universe. As time passes and expansion continues, the De Sitter horizon remains at roughly constant physical distance, while new regions cross it from inside to outside, disappearing from view as expansion carries them beyond the point where their light can reach us. Eventually, only objects gravitationally bound to our local region, primarily the merged Milky Way Andromeda galaxy and its satellites, will remain visible. Everything else will have receded beyond the horizon, its light redshifted to undetectability. Future observers, if any exist trillions of years hence, will see a nearly empty universe containing only their local galaxy surrounded by darkness. Without access to records of current observations, they would have no way to know that billions of other galaxies once filled space, now hidden beyond an impassable informational barrier. Their measurements of cosmic expansion would find only the local group, insufficient data to reconstruct the universe's history or determine its large-scale properties. This scenario raises philosophical questions about the nature of scientific knowledge. If future observers cannot access information about the broader universe because expansion has hidden it, does that information still exist in any meaningful sense? The universe has not destroyed the distant galaxies, merely removed them from causal contact. But without any possible observation or interaction, whether direct or indirect, their existence becomes empirically unverifiable. One might argue they exist objectively regardless of observability, just as we assume regions beyond our current horizon exist despite inaccessibility. Or one might adopt a more operationalist stance, holding that existence claims require at least potential observability, making statements about eternally unobservable regions meaningless, or at best metaphysical rather than scientific. These considerations about horizons and observability connect to information theory and the ultimate limits on computation and communication. The Bekenstein bound, derived from black hole thermodynamics, places an upper limit on how much information can be contained within any spherical region. The limit depends on the region's radius and total energy, with larger regions able to store more information, but only up to the point where the energy density becomes high enough to form a black hole. For a region the size of the observable universe, the Bekenstein bound yields approximately 10 to the 120 bits of information, far more than the number of atoms, but still finite. If this bound represents a fundamental limit rather than merely a theoretical curiosity, then the observable universe's information content is finite, despite its enormous size and particle number. Fundamental limits on measurement arise not from technological inadequacy, but from the structure of physical law itself. The uncertainty principle represents only one such limit, constraining simultaneous knowledge of conjugate variables like position and momentum or energy and time. But other limitations emerge from relativity, thermodynamics, and information theory, creating boundaries beyond which knowledge becomes impossible regardless of experimental sophistication. These limits shape what we can learn about cosmic scale, placing ultimate barriers on our ability to map the universe's full extent, or determine whether it is finite or infinite. The speed of light imposes a strict causal limit on information transfer. No signal can travel faster than light in vacuum, meaning events separated by more than their light travel time cannot influence each other. For the universe as a whole, this creates the cosmic light cone, the boundary between events that can affect us and those that cannot. Everything beyond our past light cone, the set of events from which light could have reached us since the Big Bang, remains causally disconnected from our present state. We can observe events on our past light cone, receiving light they emitted long ago, but cannot observe events outside it or interact with them in any way. This limitation is not technological but geometric, built into the structure of space-time itself through relativity's requirement that cause must precede effect and information cannot propagate faster than light. Quantum mechanics adds additional measurement constraints through the complementarity principle. Certain properties cannot be measured simultaneously because the act of measuring one necessarily disturbs the other. Measuring a particle's position precisely requires confining it to a small region, which imparts uncertain momentum through the disturbance. Measuring momentum precisely requires observing the particle over long distances, rendering its position uncertain. These are not limitations of measurement apparatus, but fundamental properties of quantum systems. The particle does not possess definite simultaneous values for position and momentum. Asking for both is like asking for the exact number of sides a circle has. The question presumes a definiteness that does not exist in nature. For cosmological observations, quantum limitations become relevant when considering the ultimate precision with which distances or expansion rates can be measured. Determining the Hubble constant requires measuring distances and redshifts for multiple galaxies, each measurement subject to quantum uncertainties in photon detection and timing. While these uncertainties remain negligibly small for individual measurements, systematic effects accumulate across large samples. The finite number of photons received from distant galaxies limits how precisely their properties can be determined, with statistical uncertainties scaling as n the square root of photon number. Extremely distant galaxies might emit so few detectable photons that their properties can be measured only crudely, regardless of telescope size or exposure time. Thermodynamic considerations impose limits on computation and information storage. Landauer's principle states that erasing one bit of information generates at minimum a specific amount of heat, proportional to temperature. This requirement arises from the second law of thermodynamics, which demands that entropy cannot decrease in a closed system. Erasing information reduces entropy, so compensating heat generation must occur to maintain the second law, For a computer operating at room temperature, this minimum energy is tiny, far below the energy dissipated by actual electronics. But it represents an absolute floor below which no computation can proceed without violating thermodynamics. As computers approach this limit through miniaturization and efficiency improvements, heat dissipation becomes the dominant constraint on processing speed and density. Applying these limits to cosmological data analysis suggests ultimate constraints on how much information can be extracted from observations. Processing data from the cosmic microwave background, which consists of measurements from millions of sky positions across multiple frequencies, requires computational resources that scale with the volume of data. If the data volume exceeds what can be processed within the age of the universe, using all available energy, then some information necessarily remains unanalyzed. For realistic observations, this limit lies far beyond current technology, but it exists in principle. A sufficiently detailed map of the entire observable universe, recording the state of every particle, would contain roughly 10 to the 120 bits of information. Processing this data even once, performing a single logical operation on each bit, would require at minimum 10 to the 120 bit erasures, generating heat that might exceed the available energy in the observable universe. These thought experiments about ultimate computational limits reveal that complete knowledge of the universe's state is impossible even in principle. The universe cannot fully simulate itself because the simulation requires at least as much information storage as the system being simulated, leaving no room for the computational overhead needed to run the simulation. Laplace's demon, a hypothetical entity that knows the position and momentum of every particle and can calculate their future evolution, cannot exist within the universe it seeks to predict. Either the demon requires additional information storage beyond what the universe contains, or it must be part of the system, and hence cannot simultaneously know and predict its own state completely. This self-reference problem appears whenever attempts are made to describe systems that include the observer, suggesting fundamental limits on self-knowledge that extend beyond practical difficulties to matters of logical consistency. The holographic principle, if correct, sharpens these limits by suggesting that information within any region is bounded by the region's surface area rather than volume. A sphere's information content cannot exceed its surface area measured in Planck units, roughly 1 bit per 4 Planck areas. For the observable universe with radius 46 billion light-years, this allows approximately 10 to the 122 bits of information, similar to the Bekenstein bound. But the holographic bound is tighter, applying to any region regardless of energy content, while the Bekenstein bound applies only below the threshold where black hole formation occurs. If holography represents a fundamental principle rather than merely an interesting property of black holes and de Sitter space, then the universe's information content is strictly limited by horizon area, making complete detailed knowledge of all events within the horizon achievable in principle, though not in practice. Observational limitations arise from the finite resolution and sensitivity of detectors. Angular resolution, the minimum separation at which two-point sources can be distinguished, depends on telescope aperture and observation wavelength. The Hubble Space Telescope achieves angular resolution of roughly 0.05 arcseconds in visible light, corresponding to about 24 nanometer separation at 1 meter distance or 250 million kilometers at the distance to the Andromeda Galaxy. This resolution allows individual bright stars to be resolved in nearby galaxies, but cannot distinguish stars in more distant systems where multiple stars blend into unresolved light. Future telescopes might improve resolution through larger apertures or interferometric techniques, but diffraction fundamentally limits resolution to roughly wavelength divided by aperture diameter. Even a telescope the size of Earth, coordinated through very long baseline interferometry, cannot resolve features smaller than microarcseconds, insufficient to see individual stars in most galaxies beyond the local group. Sensitivity limits arise from photon shot noise, the statistical fluctuations inherent in detecting discrete photons. A source emitting n photons produces statistical fluctuations of roughly the square root of n, making faint sources difficult to detect against background noise. The cosmic microwave background, though detected from all directions, carries so few photons per detector per unit time that achieving high signal-to-noise ratio requires long integration times and careful background subtraction. more distant sources emit fewer photons that reach Earth due to geometric dilution and redshift, making them progressively harder to detect. The faintest galaxies observed by the James Webb Space Telescope emit perhaps hundreds of photons total into the telescope's aperture during hours-long exposures, barely distinguishable from instrumental noise and foreground contamination. Systematic errors compound these statistical limitations, introducing biases that cannot be removed through longer observations or larger telescopes. Dust extinction along the line of sight absorbs and scatters light, dimming distant objects and altering their colours in ways that vary with dust composition and geometry. Correcting for extinction requires modelling the dust distribution, which itself requires observations subject to similar uncertainties. Gravitational lensing by intervening mass magnifies and distorts background sources, sometimes making them appear brighter or more numerous than they actually are. Weak lensing effects, though small for individual galaxies, correlate across the sky in patterns that must be carefully disentangled from intrinsic galaxy clustering. Atmospheric effects blur ground-based observations and absorb certain wavelengths entirely, necessitating space telescopes for infrared, ultraviolet and X-ray astronomy, despite their smaller apertures and higher costs compared to ground facilities. Cosmological distances themselves carry inherent uncertainties that propagate through all calculations depending on them. The cosmic distance ladder relies on calibrating each rung against the previous one, with uncertainties accumulating at each step. Parallax measurements of nearby stars achieve precisions of a few percent at best, limited by Earth's orbital diameter and the tiny angles involved. Cepheid variables add their own uncertainties related to period luminosity calibration, metallicity corrections, and extinction. Type Ia supernovae show intrinsic variation in peak brightness that must be corrected using empirical relationships between luminosity and light curve shape. Each correction introduces additional scatter and potential systematic bias. By the time distances reach billions of light years, total uncertainties approach 10 to 20%, limiting precision on quantities like the Hubble constant that depend directly on these distance measurements. Theoretical models used to interpret observations contain parameters that must be fitted to data, creating degeneracies where different parameter combinations produce similar observational signatures. The cosmic microwave background power spectrum constrains cosmological parameters tightly when all features are measured precisely, but individual parameters remain correlated. Increasing matter density while decreasing dark energy, density can produce similar effects on certain observational features, requiring multiple independent measurements to break the degeneracy. Some parameter combinations remain poorly constrained even with excellent data because they affect observations only weakly or in ways degenerate with other effects. The sum of neutrino masses, for instance, affects structure formation and the microwave background subtly, requiring extremely precise measurements to detect its influence amid other uncertainties. The problem of cosmic variance represents a fundamental statistical limitation affecting measurements of large-scale structure. We observe only one universe, a single realization of the statistical processes that generated cosmic structure. When measuring quantities averaged over large volumes, such as the amplitude of density fluctuations on scales comparable to the observable universe, we face irreducible uncertainty because we cannot repeat the measurement in different universes to build ensemble statistics. Imagine trying to determine if a coin is fair by flipping it only once. The result tells you very little because statistical fluctuations dominate small samples. Cosmic variance works similarly. Measuring the temperature fluctuation amplitude in the microwave background on angular scales of tens of degrees samples only a few independent regions, not enough to determine the underlying statistical distribution with high precision. Smaller angular scales fare better because more independent regions contribute to the average, but the very largest scales remain fundamentally limited by having only one universe to observe. This limitation becomes especially severe for testing predictions about the universe's overall geometry or topology. If the universe is finite with a complex topology, light might wrap around it multiple times, creating correlated patterns in opposite directions on the sky. Detecting such patterns requires comparing temperatures or galaxy distributions between distant regions to find unexpected correlations. but the small number of independent large-scale samples makes distinguishing real correlations from chance alignments difficult. A suspicious pattern might result from topology, or it might simply be a statistical fluctuation in a random distribution. Without multiple universes to compare, deciding between these possibilities requires assigning probabilities based on theoretical priors about which topologies are more likely, introducing subjective elements into the analysis. The Copernican principle, assuming we do not occupy a special position in the universe, helps constrain possibilities but cannot be proven observationally. We can verify that the universe appears roughly isotropic around us, looking similar in all directions, supporting the idea that we do not sit at a unique centre. But isotropy around our location does not guarantee homogeneity, the property that all locations are statistically equivalent. A spherically symmetric but inhomogeneous universe could appear isotropic from a special central position while violating homogeneity. Testing homogeneity requires observations from multiple widely separated locations, which we cannot achieve. The Copernican principle provides a reasonable assumption that has worked well historically, guiding us away from geocentric and heliocentric models toward accurate understanding of our cosmic position. But it remains an assumption rather than a proven fact, one that could in principle be wrong despite its philosophical appeal and historical success. Modified gravity theories illustrate how observational limitations allow multiple theoretical interpretations of the same data. Dark matter models explain galactic rotation curves and cluster dynamics by postulating unseen mass. Modified gravity theories explain the same phenomena by adjusting gravitational laws at low accelerations or large scales. Both approaches fit current observations reasonably well, though dark matter generally provides simpler explanations for a wider range of phenomena. Distinguishing definitively between these scenarios requires observations with precision and scope that may exceed what is practically achievable. If dark matter particles interact too weakly to detect in laboratory experiments, and if modified gravity can be tuned to reproduce observations arbitrarily well, then deciding between them becomes underdetermined by available evidence. Additional theoretical considerations like simplicity, naturalness, or consistency with other physics domains guide choices, but these criteria involve judgment rather than pure empirical discrimination. The fine structure of space-time at Planck scales remains completely inaccessible to direct observation. Probing distances of 10 to the negative 35 meters would require particle accelerators with energies of 10 to the 19 giga-electron volts, roughly 1,000,000 trillion times more powerful than the Large Hadron Collider. Building such an accelerator would require energies exceeding the total output of human civilization for timescales far longer than civilization has existed. Even if such energies were available, concentrating them into the tiny volumes needed for Planck-scale collisions would create black holes before revealing the underlying structure of space-time. This fundamental limitation means that theories of quantum gravity cannot be tested directly through controlled experiments at the relevant energy scales. Indirect tests through cosmological observations, precision measurements of gravity at accessible scales, or mathematical consistency requirements provide the only constraints on quantum gravity theories. Some theorists suggest that this experimental inaccessibility of Planck-scale physics represents a fundamental barrier beyond which science cannot proceed through its traditional methods of hypothesis testing and experimental verification. If quantum gravity effects become important only at energies forever beyond experimental reach, then choosing between competing theories requires criteria other than empirical adequacy. Mathematical elegance, conceptual coherence, and consistency with established physics at lower energies guide theoretical development, but these aesthetic and logical considerations differ from the experimental tests that have historically driven physics forward. Whether this represents a temporary limitation awaiting clever experimental approaches, or a permanent barrier intrinsic to studying physics at the smaller scales remains debated. Some remain optimistic that indirect tests will eventually distinguish between quantum gravity proposals. Others suggest that multiple consistent theories might exist, all reducing to identical predictions at accessible scales, making the choice between them ultimately arbitrary or metaphysical.